Well, good morning, everyone. Thank you for joining us. We're going to host here a tutorial on the Globus Compute platform, which is a new product offered by the Globus team here at the University of Chicago and Argonne National Lab, which is focused on running computation in much the same way that Globus currently manages data transfers. So by way of introduction, my name is Kyle Chard. I'm a research associate professor here at the University of Chicago. I co-lead our research group, which is got a bunch of students and postdocs and others in it that really are researching everything fairly broadly around distributed systems and scientific computing. Yadu, do you want to quickly introduce yourself?
Hi everyone. My name is Yadu. I am a research engineer at the University of Chicago, and I work on workflows and scientific software. Basically, I work on Parcel and Globus Compute. Reed?
Yeah, my name is Reed Mello. I'm an engineer on the Globus Compute team. Yeah, I'm also a Parcel contributor, but I sort of work on the product that is Globus Compute.
So by way of quick introduction, Parcel is a parallel programming library for Python that we've worked on for the last 7-ish years, and Globus Compute builds very heavily on Parcel to deliver its compute capabilities. So we'll talk about that a little bit as we go. The other thing, we've got a nice sized group here, so I would encourage people to just yell out as we go with questions. I was saying to Yadu before we started, I often find these virtual tutorials are very they can be very quick and very not very engaging, because you don't get to see if people are struggling. You don't get to see if people have a look on their face like, what does that go on about? That sounds a bit crazy. So I would very much encourage you to yell out if you've got any questions as we go. We can basically take this in any direction you like, so we can customize examples to specific types of patterns that you're interested in, et cetera, et cetera. At some point, it might be worth as well talking a little bit about your backgrounds and sort of where you're coming from, because I think when we give this tutorial, we have we often have sort of two quite different communities that are interested. So there's the user community that really want to think about how they take their application and run it with this platform. And then there's the administrator community, which is interested more in how do I deliver or use my resources, expose them in this sort of function as a service way to the community. And the types of questions and interests are, of course, a bit different between those two groups. Okay, well, let's get started. So by way of outline, assuming I followed the instructions correctly, we have an hour and a half before a break. So we're going to do a quick introduction where I'll tell you a little bit around the motivation and high level about what we're trying to achieve with the Globus Compute platform. We'll then spend half an hour, Yadu will lead this talking about the SDK. So this is the user, researcher, scientist perspective of using Globus Compute. Yadu will run through a Jupyter notebook, which you all can run through without installing anything on your laptops or PCs or supercomputers or clusters or clouds. Then we'll do basically an hour broken up by the break talking about endpoints, and Reed's going to lead this discussion. So he's going to start by telling you how you can install a single user endpoint on your laptop or on your allocation on an HPC system. And then after the break, we'll come back and talk about our newest offering, which is a multi-user endpoint. So for those that are familiar with Globus, on the data side, single user endpoints are Globus Connect Personal, multi-user endpoints are Globus Connect Server model. And so we'll dig a lot there into the administrative functionality that's supported by the multi-user endpoint. We'll then have a half an hour on real scientific applications. So we'll go through a machine learning workflow where we're using a machine learning model basically to steer a simulation experiment. I'm trying to remember which one I picked. I think I picked the molecular design application, but we'll find out when we get there. I'm pretty sure it's the molecular design application. You see there's a chat question. Okay. And then we'll have half an hour at the end for a discussion. So basically, this is your chance to ask anything you want. How does this map to your use case? How doesn't it map? What would you love to see in the platform? We are still fairly actively developing it. So we have a team of developers here at the University of Chicago and Argonne and the Globus group who are building this out. So this is a prime time to be asking for new features. If it doesn't quite match what your use cases are, we'd be happy to think about that. Okay, let's get started. And I assume someone would have told me if I got the schedule wrong, if I didn't line this up right, but I'm pretty sure this is right. Okay, so first, before we start, we like to start by introducing what Globus is. So very briefly, Globus is a non-profit service that's developed and operated by the University of Chicago. So we're a group within the University of Chicago. You've probably heard about Globus, particularly on the data side, because Globus is very widely used. I think it's deployed on about 60,000 endpoints around the world, has roughly 600,000 users, moved several exabytes of data, fairly pervasive in the research computing space, particularly here in the United States. Our mission is to try and make it easy and efficient for researchers to engage in their data-driven science and scholarship through offering sustainable software to the community. So really, we're very strongly motivated by challenges that researchers face in their day-to-day life. Our goal really is to try and make it to sort of raise that level of abstraction, so researchers themselves are not dealing at the minutiae, at the very fine-grained details of having to do sort of sit there and babysit a data transfer, sit there and babysit running a large simulation over several days across supercomputers, et cetera. So really, we're focused on all of these pain points that people face in their day-to-day life, researchers face in their day-to-day life, and trying to provide a set of cloud-based services and a cloud-based platform on which they can exploit the capabilities that we provide to the community. I'm going to stop clicking on things. So let me start with some context of why we're focused on computation at the moment. So there's this great quote here from a paper in the Communications and the ACM now 2 or 3 years ago. And there have been a few papers with similar types of observations recently, but I think this puts it very, very nicely. So I'll quote it verbatim. "The economic cycle that has led to the usage of a common computing platform underpinned by rapidly improving universal processors is giving way to a fragmentary cycle where economics push users towards divergent computing platforms driven by special purpose processors." So this has really been a long time sort of in the works as the research infrastructure is evolving, right? No longer are all our applications running on a CPU processor sitting there in our laptops or in a PC under my desk or even on a shared HPC system. Instead, we're seeing a much more diverse computing infrastructure. Some of this is, of course, motivated by the slowing of Moore's law. We can't just jam more and more transistors on a piece of silicon at the rate we've been able to in the past. We can't just assume that every 18 months our computers are going to be twice as fast and our applications are just going to benefit from that rapid growth in terms of computing capacity. But instead, now what we're reliant on is more heterogeneous, specialized computing elements, right? We're starting to see an evolution in terms of the pervasiveness of GPUs for many of our analytics and machine learning workloads. We're seeing specialized processing elements for machine learning training and inference. We're seeing even adoption of things like FPGAs and custom ASICs in different domains that are really trying to squeeze all that performance out of the actual computing elements we have. And of course, as we imagine this world in which resources are becoming more specialized, resources are also becoming more distributed. It's not feasible for me to have one of every type of resource in my office here at the University of Chicago. Instead, I must make use of computing resources that are out there in the wild. I make use of Access resources. I make use of my department cluster. I make use of my institutional research computing center. I make use of DOE supercomputers. I rely on clouds, Chameleons, Jetstreams, Amazons frequently in my work. And so by this sort of evolution of the research infrastructure, essentially all of our scientists and researchers must now think about being able to dispatch their computation across this computing continuum of capacity that's available to us. So now, when we started on this process of building out the Globus Compute platform, which was previously called FunkX, if you're wondering why this sounds a lot like that platform that you've heard about before. We looked at 3 sort of big changes that we were seeing in the community. So the first is, as I said before, that the computing infrastructure is really becoming more specialized, and because it's becoming more specialized, it's becoming more distributed, and therefore people are needing to make use of remote computation more generally than they have before. The second thing we see is that workloads have changed a lot in the last decade. We're seeing a lot of interactive real-time workloads. We're seeing people use Jupyter notebooks where they're doing back and forth computation analytics type analyses. We're seeing people plugging computation in at the end of an experimental process where they've got data being acquired from an instrument and needing to be processed very, very quickly. We're seeing workloads that involve collaborative groups of people that are working together to perform their analyses. We're seeing, of course, widespread adoption of machine learning methods, both in the training and the inference side, particularly in fairly diverse scientific applications. Anything from real-time on-demand stuff, where we can run a very rapid machine learning algorithm to detect the quality of a sample, through to simulations where we can use lightweight machine learning surrogates to help us screen a much larger search space of potential candidates for a particular task, or even machine learning algorithms to help us steer our experiments, to the active learning loops that guide our both physical and simulated experiments. The result of these workloads, if we start to imagine them being composed of these much smaller pieces, are that we can potentially obtain performance benefits, energy benefits, by way of breaking up those elements and running them in different places. So we see here at the bottom this plot of runtimes for a bunch of different scientific applications here, anywhere from on the leftmost is a text tabular file system, file extraction, where we're going through text and extracting files, that's running for on the order of less than a second, through to scientific applications there, tomography, preview, dial stills processing, correlation spectroscopy. These are all analyses for beamline data coming off the advanced photon source. And you're seeing these types of functions running for seconds, less than a minute. In other work, which I haven't included here, we've done some experiments where we've broken up applications and run them across department cluster, PCs, and national cyber infrastructure, supercomputers, and clusters. And we've shown that we can actually break up the applications into pieces, run them in different places, and be able to not only reduce the energy of those applications, the entire application, but also increase the speed that the application runs. So we can get some significant benefits from being able to break up the pieces and run them in different places. The benefit, of course, being by running in the most appropriate place, we're able to better align the needs of the task that needs to run with the capacity of that computing element. Similarly, you can get benefits from running in the best place around data location. So running a task near the data may very well be faster than needing to move the data to where the task runs. And of course, if you've been around the cyber infrastructure space for a long time, you will have heard that story for many, many decades. And then the final thing we see is that users are changing. So a decade or more ago, we had a lot of people that were running on HPC from the high energy physics domains, potentially the biology domains, materials. Now we're seeing much broader use of very diverse, specialized, high performance computing elements from a much more broad user community. We've had people like archaeologists running network analyses. We've had people dealing with evolution of language, needing to train machine learning models, right? So we're seeing a very, very broad adoption of these types of resources. It's now becoming increasingly critical for researchers in many, many domains to be able to make use of these types of resources. And with that come the types of environments they're used to working in, Jupyter notebooks, etc., where they're able to craft their analyses, and they would like to ideally continue to work in that environment, but just augment that environment with the resources they need to conduct their work. I should really hurry up. Similarly, our Globus legacy is also morphing. So we originally started out focused very much on fast, reliable data transfer. We then moved to provide secure in-place data sharing. More broadly now, we provide sort of data management across the distributed ecosystem of Globus endpoints. We're providing automation capabilities, so you can have cloud-hosted workflows that do things like acquire data from instrument, move it to analysis, to an HPC system for analysis, publish results in a search catalog, et cetera, et cetera. So the Globus platform itself is becoming equally diverse in terms of the capabilities it provides. And what we've tried to do here with Globus Compute is to provide that same fire and forget model that has been so successful over the last decade to the computation space. So ideally, users are able to say, Globus Cloud Platform, please take this big workload I need to run and run it on a bunch of different computers in different places. My lights just turned out, sorry, in here. If I don't move enough, the lights in my office turn out. So let's take a step back and think about some of the complexities. We talk about fire and forget. Why on earth would we want fire and forget for computation? And we've got a list here of some examples of some of the things you as a user need to take care of when you're trying to remotely perform a computation. The first thing you need to do is work out how to authenticate. This becomes, of course, even more problematic when I'm using two HPC systems in different domains. I've got two different accounts. I've probably got two different authentication models that I need to deal with. I've got an access credential, a local credential. I've got SSH keys that are probably now blocked out, and instead I have to use 2FA in different places to connect. I need to then maintain a persistent connection to those resources. So I SSH into my resources ready to run my computation. I need to then know how to provision resources. So this can be very different depending on the types of scheduler or cloud API that's exposed by the resources I'm connecting to. I might have a Slurm cluster. I might have a Kubernetes cluster. I need to know how to represent the type of job I want to submit. I need to submit that job for execution. Wait for the job to get time, try and decipher the strange priorities I'm assigned to work out when I'm actually going to get my resources. Once my job is running, I have to go and configure my execution environment. I have to load a bunch of modules. I have to set up Python environments such that my job will run. Inevitably, things will break. The number of times I've set a job in a queue, I've tested it on the debug queue, I'm pretty confident it's going to work. Starts running on 100 nodes and immediately breaks because of something that I just hadn't considered at the time, right? So as a user of these big systems or these distributed specialized resources, I need to understand how to even identify when there are problems, recover from them very quickly, and be able to continue with my research without having these very long periods of downtime between my computations. And of course, every time I move to a new resource, or every time even, I mean, much like the Globus story of data movement, I'm not doing this every day, right? But if every couple of weeks when I need to try and run my computation, I've got to overcome similar obstacles. It's very rare that things will just work the next time I log into a system. So this brings us to Globus Compute. So in a one-slide description of what Globus Compute, it's a function as a service system for any compute resource. By function as a service, we mean register a Python programming function with our cloud service, and then be able to run that Python programming function one time or 1,000,000 times on the resources that are connected to it. Globus Compute here sits as a cloud-hosted platform using the Globus hybrid model, right? So we run a cloud platform. That platform is not responsible for doing the compute itself. We don't give any cores or cycles to actually run the computation. What the platform does is it provides that middleman service that enables me to route the computation to run in a remote location. We'll babysit that execution of the computation and then return the results back to the user when they're ready. The sort of outer band here, I don't know if you can see my mouse, but this outer band on the loop here is showing the types of resources that are exposed by a particular computer. So here we're supporting laptops, HPC resources, commercial clouds. These have a variety of scheduler interfaces or API interfaces via which we get resources, anything from Slurm, which is very common, to PBS or Condor or Kubernetes. On these resources, we layer a Globus Compute agent. So this is the Globus Connect software, but for computation. And then that exposes that resource to the Globus ecosystem to run computation. So what we provide then with that cloud service is this fire and forget reliable execution. You can basically say, here's my batch of jobs. Please go ahead and execute them. If the resource that I want to execute them on is offline, the cloud platform will just hold those tasks ready to run. When the resource becomes online and available, it will start sending those tasks down for execution. So effectively, we're taking away a lot of the pain of dealing with this very diverse, heterogeneous ecosystem for execution. Of course, this is providing, the Globus Compute agent provides a consistent user interface across these different batch schedulers, and we provide a very simple Python API, an asynchronous Python API, to be able to execute these functions in different places. So you don't need to change your applications when you move between different resources, irrespective of the type of resource or the scheduler or API provided by that resource. So let's take a closer look at what this looks like. So Globus Compute is made up of a couple of different things. It has this compute service, which is this highly available cloud-hosted service run in the sky. This is hosted by our team. It makes use of a lot of Amazon services under the covers that are very scalable, reliable, secure. It uses everything we've learned from the Globus data side, where we're running things in a a replicated way such that we're able to achieve very high availability and reliability of the service. The second thing we have is an ecosystem of Globus compute endpoints. These are the deployments of those agents that I just mentioned that abstract access to the different computing resources. And then finally, we have an SDK, a software development kit written in Python that provides an interface for interacting with the service. It looks very similar to other parts of the Globus SDK. So let's look at what this looks like from the researcher's point of view. So we have here a couple of compute resources. We have a resource A and a resource B. This might be a supercomputer running an access supercomputer like Expanse or Delta. This might be a local research computing center. On both of them, we have a Globus compute agent set up, and we have here a happy little researcher who would like to run their computation. So what they do is they basically just ask the Globus compute service to execute a function on resource A and resource B. Globus compute will wait for these endpoints to be ready. When they're ready and connected, it will then send the task down for execution. It will provision resources from that resource, run the task, retrieve the results, send them back to the Globus compute service, and then at a later point in time, the user can come and grab those results. We keep the tasks and results in the cloud service for about 2 weeks. So it gives you a lot of wiggle room in terms of resources being online or you coming back again to grab the results. So the first thing I want to talk about here is the Globus compute agent. So this is the piece of software that's deployed on the computer to make it accessible to the Globus compute platform. This is a very fairly lightweight piece of code that, as I mentioned in the start, builds upon the Parcel Python parallel programming library for how it actually communicates with resources and provisions resources, provisions nodes, etc. It's a pip installable, so the single user agent is entirely Python based and it can be pip installed locally. We also have native packages for Debian and Yum for our multi-user endpoint. This software basically supports, as I said before, a bunch of different schedulers and APIs for provisioning resources. What does this look like from a user's perspective? I said it's entirely pip installable. So you see a couple of lines here. I pip install my Globus compute endpoint. I Globus compute endpoint configure my own endpoint. Once it's configured, I can start that endpoint up and then I can start dispatching tasks to it. Okay, so I've started it there. The one question you might ask, well, how does this authenticate? There's a step that's not shown here. The first time you start this thing, the very first time you start it, it's going to ask you to log in. You'll go through the normal OAuth flow, Globus OAuth flow, and enter a token here. That will then securely peer that endpoint with your user account such that you're the only one that's able to execute tasks on it. So this is the single user endpoint. Reid will explain later how the multi-user endpoint works, where an administrator can deploy it and then any user who has access to that system can use it. What does it look like from the user side when I actually want to run something? So as I said before, we provide a Python SDK for running tasks. We have two sort of main interfaces via which you can run tasks in this FAS ecosystem. The first is a traditional FAS interface where you register a function, you get back an ID for that function, and then you can invoke that function by ID. The second way we provide, which is the sort of default, the more common way we see people use the Globus Compute SDK, is through the asynchronous executor interface. So we implement the Python standard concurrent futures executor API. And what this allows us to do, basically I can import an executor. I provide the ID of that executor, which I was given when I provide the ID of the endpoint, which I was given when I started the endpoint. I then instantiate the executor just with that endpoint ID. And now what I can do is just asynchronously submit functions to run. So I define a Python function. I can now just submit it to run. I want to run hello world with 1 or 2 or 3 or 100 different arguments, submit it. What I get back is a future. A future is an asynchronous construct. It's basically a reference to that result. So the computation here has not blocked. Instead, here I have a pointer to that result, which I'm going to be alerted of when it's completed and ready to come back again, right? So I can actually connect to that thing, wait for it to be completed, and then retrieve the result and do something with it. Given it's an asynchronous contract, I can create a loop here, run my submit 1,000,000 times, store a list of futures, grab the results when those futures are finished. Saw some chat messages there. Reed's handling it. Okay, good. Feel free to yell out if you've got questions as well as we go. I can't see hands, so you just have to make some noise and I'll hear it. Importantly, these endpoints, I didn't mention this before, but importantly, these endpoints are designed such that they can be deployed in different environments. They make outbound network connections only. So they'll work in environments with firewalls. They'll work in environments with NAT. They're basically making connections out on 443 SSL out to our cloud service to be able to request tasks when they're ready. So we run these endpoints on most of the DOE and NSF supercomputers. We run them on things like Raspberry Pis. We run them on laptops without any issue with where they're deployed. We also have a web API for interacting with some of the platforms. So this is the thing that we're most actively working on at the moment. So at the moment, the web interface allows you to search for and manage your endpoints. You can see here information about endpoints that are running in terms of the statistics. You can see things around the configuration of that endpoint, so you know how it's configured, what resources are available to it, etc. Usage is growing rapidly. So this is a plot showing when we sort of first started the NSF project around 2019. You see here we had a handful of users. That was probably Yadu, me, and Reed. Through to now, where we have more than 1,000 people actually running functions with Globus Compute. We have a large number of endpoints now available. So this is, I think we have about 12,000 endpoints, a little more. And we've run on the order of about 42 million tasks as of when I pulled this data a couple of weeks ago. So we've still got 3 months left in the year, so hopefully we'll be a little bit higher. But you can see the tasks are growing nicely, users are growing nicely. At the bottom here, we have a picture from last week or the week before, our annual Parcel and Globus Compute user meeting. So we joined these into one meeting because the communities are overlapping. I think we had north of 100 people registered. I don't know how many people are in this picture, but about 60 or 70 people in person. I'm going to talk in the next few slides about how people are actually using the platform. We see a number of sort of fairly similar or common use cases that people are adopting, from running a bag of tasks, automating their research, or increasingly actually building other services on top of the Globus Compute platform. So one example here is around the sort of bag of tasks type style workload. So we've found people find this to be quite a useful platform when they have a stack of things they want to run, where these things look relatively similar, right? I want to run, in this case, this was during work in the 2020 range, exploring potential therapeutics for the COVID-19 pandemic. The story is that we had many molecular databases. We wanted to screen those molecular databases for candidates that might be good therapeutics. So basically, researchers developed a bunch of functions. Each one of these blue things is a Globus Compute function that would run. It would canonicalize the format of the SMILES string. So again, this is beyond my pay grade, but there's some differences with how these molecules are represented. So this turns it into a common way. They would compute features of these molecules that they use for machine learning algorithms. They would compute fingerprints and images that they also use for machine learning algorithms. And then they could run things like similarity search on the fly. So they basically ran big batches of these billions of molecules as a set of functions that were running on a number of computing resources that were made available at the time. Second example, which is what we're going to talk about at the end of this tutorial, where we're going to do a hands-on machine learning workflow. In this case, using AI as a wrapper or a loop around a large bag of task applications. So this example here is trying to screen or test a bunch of different molecules for those that might have a characteristic or a capability that would be useful for a particular application. In this case, energy storage. The problem that people try and overcome here is that there's far too many molecules to spend time doing exhaustive simulations. So instead, what people are interested in doing is build these active learning loops where they run a simulation on a small number of candidates. They then use those simulated results to build a machine learning model that they can then use as a lightweight surrogate for the entire search space. So they can go and run this machine learning algorithm on a lot of different candidates, go and pick the ones that perform best. The ones that perform best then go and run an actual expensive computation on it to get a more accurate measure of its capabilities. So we'll come back to that in a couple of hours. The other thing we see a lot of is use of Globus Compute in automation scenarios. So I mentioned before that Globus has a service called Globus Flows that allows you to connect together different actions into these workflows that are managed. They're represented and managed entirely by a cloud service. And so each of these actions is occurring potentially in different locations. So we have here an example of an application. I expect it looks like a scattering application from the APS. And what we have here is that the flow first launches a QA job that's running near to the instrument that makes sure that the data coming off is of reasonable quality to spend the rest of the cycle. We'll often have something like a human in the loop here where a researcher needs to check it and say, okay, that looks good. What we'll then do is we'll transfer the data to an HPC system for analysis. We'll run a much bigger analysis here, trying to understand characteristics or reconstruction of what we're trying to sample. We might visualize it in a way that we can send back to researchers. We might gather some metadata such that we can index it, and then we'll transfer results back again to some sort of globally shared location where researchers and their collaborators can look at the results of the experiment as it's ongoing. And so you see here that these compute steps, the 4 of them, are running in different places as needed by the data transfer by the science experiment that's running. More examples of common use cases. So why are people using this? One, it makes it easy to scale from a laptop to a cluster, to a cloud, to a supercomputer. It makes it easy to move between different resources to which I have allocations. It makes it easy for me to drive my computation from a workflow like I saw before, or from my laptop, or from a Jupyter notebook. I'm benefited by the fact I can outsource a lot of the complexity to this cloud platform and just come back and grab results when they're finished. I thought I had an example here of building a platform, but I don't. We're seeing a lot of people building gateways on top of Globus Compute, where it enables them to provide a customized portal to their community, but then run computation in the back end behind it. So we've got some examples there in Earth systems, in cosmology, biology, et cetera, that are using this platform. And then finally, as part of automated flows, as I mentioned on the previous slide. Very quickly, a word on sustainability. So Globus implements a freemium model. The key point I want to make here is that core Globus functionality is always and will always remain free to the research community, right? So users are able to use 99% of Globus capabilities with no cost, no subscription required. We do have a subscription model. This is crucial for us to be able to provide the service to the community. You can see that we use a lot of cloud resources. We have a team of amazing developers, software engineers that are building, maintaining, responding to pager alerts in the middle of the night to try and make sure these services are as reliable as needed to base your research on it. Subscriptions are for institutions only, or institutions and companies. So most of the I think we have about 200 subscribing institutions around the world. Most of the R1 and R2, maybe not most of them, but many R1 and R2 institutions are subscribers. Those subscribers have access to advanced capabilities that are typically targeted towards administrators. So advanced capabilities around managing and controlling data movement in and out of your resources. At the moment, Globus Compute does not have any functionality that is part of subscription, but we are starting to think about what an administrative console would look like for managing multi-user endpoints, providing more high assurance policies, et cetera. So in the future, we'll probably build out some subscription capabilities, but it will be entirely focused on administrators. The capabilities you have now as a user will continue to be free. I should say thank you to the many people that have funded this, particularly the NSF that gave us a CSSI award to build out the FunkX platform, and as part of our sustainability model, then transition that into Globus Compute. Okay, with that, I'm done. Does anyone have any questions, or has Reid handled those while we're going? I'll take that as a no. We'll get on to the more interesting. Oh, there's a question.
You've got a question.
Does the idea of moving your compute to the data instead of vice versa play any role? So this is 100%. This is a really big goal for us, is to be able to reduce costs, improve efficiency of computation, reduce things like energy. So being able to move the computation to the data is a huge goal of the Globus Compute platform. We don't have very tight connections yet between the Globus Compute functions and Globus Compute data transfer, but we're deploying Globus Compute endpoints in the same places you have the Globus Compute data, Globus Connect server, so the data access. So the hope is that we'll be able to build some more intelligent sort of interplay between the two worlds. It's a good question. Okay, let me hand this over to Yadu.
All righty. Let me make sure I can share and get started. Quick check. Are you guys seeing my screen in its completeness? Okay. There's no weird box on the side. Okay, let me just try and like get rid of that box. Okay. All right, cool. So I won't be able to see chat properly now that I've minimized everything else. So please stop me and raise your voice if you have any questions. What I will be covering is basically Globus Compute 101, the introduction to how, as a user, you would interact with Globus Compute. So to okay, cool. Yeah, to begin with, here is basically as a fast system, how you would interact with Globus Compute. The primary mode by which you would interact with Globus Compute is through functions. And by functions, we are talking about Python functions in general. So the mechanism is always that you would register a Python function, do that with the Globus Compute service. You specify the input arguments and you specify the target endpoint where you would like to send that function off to. Once that is done, Globus Compute does the job of storing the task, like piping and buffering the task, waiting until the endpoint is online. And once the endpoint is ready, it would fetch the task, provision resources from the machine. So assuming your endpoint is running on a campus cluster or a supercomputer, when the task gets to the endpoint, it decides, oh, I need more resources. It goes and negotiates with the local system's scheduler. So if it is Slurm, PBS, Torque, whatever it is, it will negotiate with that system, provision nodes that are required for running the function, and then execute the functions. Now, once these functions are run, the results produced are shipped back to the cloud, and we store them there. Like Kyle said, we have the results stored in the cloud for up to 2 weeks. Now, the users can retrieve the results asynchronously. These functions are also shareable with collaborators. The next bit that I want to get into is the details of exactly how you do all of that, especially from the client side, where you use the Globus Compute SDK, which is a Python package that you can install and import, and then use as you would like in your Python scripts. So the first bit is the Globus Compute SDK itself. So you can pip install the Globus Compute SDK. It's available in PyPy. And this is the preferred mechanism. The Globus Compute SDK's executor is the preferred mechanism by which you would submit tasks and interact with Globus Compute. There is a second method, which is the Globus Compute SDK's client mode, where you would be interacting more using the fast style model, where you would register a function, get a function ID, submit that function with a bunch of arguments and a target endpoint, get a task ID back, and then wait on that task ID separately. So that's the more fast-like model that you might be familiar with if you are used to using AWS Lambda and such. The SDK's executor method is more Pythonic in that if you have experience using, say, the thread pool executor or the process pool executor or any of the computational platform solutions, for example, Dask or Ray, you would be familiar with the executor. So the compute SDK's executor gives you that familiar interface to interact with the Globus compute system. So as you can see on the right side, there is this little blurb which shows you how you would specify this. So all you need to tell the executor is the target endpoint ID that you would be shipping your functions off to. So you specify the endpoint ID, get the executor, and you can say submit functions to that executor. Once you submit a function to the executor, what you get back is a feature. And this is the key bit if you're not familiar with executors. Executors are a mechanism by which you can submit a function to the executor for execution, and you get back a feature, which is a proxy for the function executing somewhere off in the background. So you have shipped out the function to Globus Compute for execution. You get a feature back, which is like your token that tracks the result of that execution. What this lets you do is multiple asynchronous function executions in the background. So you could submit as many functions as you want, collect all the features for the functions that you submitted, and then asynchronously wait for that. Now, the executor that we are using, it's basically subclass from the concurrent features executor class. It's the standard popular method for doing this sort of asynchronous execution in Python. And just to note, while you can use the executor without using it as a context manager, it's best practices to use it as a context manager so that there is efficient cleanup afterwards. So as I mentioned just a bit back, when you submit a function to an executor, what you get back from the executor is a feature. Just to cover all our bases, a feature is a concurrent features future object. It's asynchronous computing primitive. And what it does is it gives you two different mechanics to wait for the result of an asynchronous execution. If you say future.result, that basically blocks and waits until the result is available. You can obviously also put a timeout on that. You can say .result timeout is equal to n seconds and wait for that long. Alternatively, you can also just say future.done, which basically gets you a Boolean immediately without blocking, whether the result is ready or not. So this primitive basically lets you stack a bunch of functions that you have submitted for execution remotely and wait for them as you please. Right? So to put all of this together, here is how you would do a very simple basic execution. To begin with, what you need to do is import the executor. So you would say Globus Compute SDK import executor. You would create a function. In this case, this is a very simple function that takes a float and an integer, multiplies them, and adds a random number to it. You create the executor, like I mentioned earlier, with a context manager, where we would say with executor. Okay, just to make sure, you need to also put the endpoint ID in the executor's path as GCE. So you get the executor started up, and you can say submit the functions. Now, what I've done here is rather than specifying the endpoint ID when I instantiated the executor, I have set the executor endpoint ID on the fly. I put this in this example here just to show you that during the execution, you are very well allowed to change the endpoint ID that you would like to target your functions to. So you could very well write a loop where you submit one function to one endpoint, the other function to a different endpoint, and so forth. So the submission of the functions in a loop, what I'm doing is I've basically, I'm taking the sysRB, so whatever is supplied to the function, supplied to this Python script as it is invoked, it is taken up. You create a list of tuples. and then you submit that to the jittery multiply function that we defined earlier. So you get a list of features back from this submission, because this simple list computation will iterate over this zip expansion and will give you a list of features that you would then iterate on and wait for. So there are two options that you could do here. You could put a loop and wait for each feature one at a time, or you could use the concurrent features as completed method, which takes a features list. This basically lets you say that I've submitted these features, give me the first feature that is done, and so forth in order of completion of the features. So rather than waiting for one feature after the other in order of the features in the list, you can wait for the features as they complete. And now, to put all of this together, when you execute this little Python script, Python jittery multiply, and give it a few different numbers, we get those outputs generated remotely from whichever endpoint that we have targeted to. It would run those functions there and get you back the results. So how does all of this happen? The basics of it goes somewhat like this. The compute executor takes your function, serializes it, arguments and such, ships it to the web service for execution. The web service will enqueue that task into an endpoint-specific task queue. Remember that when we submit the function, we specify here's the function, here's the arguments, and here is the endpoint that this function should execute at. So when the functions are submitted, the web service knows exactly which endpoint to send the function to. The endpoint task queue is listened to by the compute endpoint. So then the compute endpoint would be listening to this endpoint task queue, assuming it is online. It would consume those tasks, run those tasks, and when the results are produced, it will enqueue those results into the task group's result queue. Now, the compute executor is pretty efficient in that there is a listener that is connected to RabbitMQ listening for the specific session that it is submitting task over. So these results would immediately come back rather than polling the service for each result every so often. This is very good for latency in that we would immediately get results as soon as results are available in the RabbitMQ pipe. So the results will be immediately consumed by the compute executor and presented to you back over the features. So this is basically what happens under the hood. Just to make sure, at this point, does anybody have questions? Okay, cool. I'm going to go to the next one then. So at this point, what I want to do is show you this Jupyter notebook that will allow us to go over our very simple compute introduction notebook and go over all of the stuff that we just talked about. If you have spare cycles, please take this link. You can also scan this QR code to get to this. It's basically jupyter.demo.globus.org. And I will walk you through a live session of going over the tutorial notebook. Okay, just so everybody sees exactly what is supposed to happen, I'll just pop this up. So, goes to Jupyter Lab. I'm already logged in, so I cannot show you the login flow. But essentially, you log in with whatever Globus credential that you have. And you basically want to be opening up this notebook. So at the top, there is a Globus Jupyter Notebooks. And from this, we want to be using the compute introduction in case anybody is following along and trying the notebook along with me. Just so that you guys know about this, when you logged into the Jupyter Lab, you had to authenticate, and those same authentication credentials are stored in the session. And those credentials are read into this notebook using this block of code right here. I know it looks a little bit ugly, but Otherwise, you would have to redo all. That's the whole point of this block, to avoid having to do that again. So I'll show you how this goes. So the first bit and the most important bit is make sure you've got Globus Compute SDK installed on the client side, assuming that you're running on Jupyter Notebook. You don't have to do all of this because the environment is already set up with all of the required packages. But if you are trying to run Globus Compute from a standard Python terminal, make sure you have the Compute SDK installed. Make sure to match the Python environment between your client environment and your target endpoint ID. Your target endpoint. If your endpoint is running Python 3.11, make sure you run the same Python version. This will make sure that you do not run into any serialization bugs along the way, because Python serialization across versions is still very difficult. So here we go. So I'm going to import the required packages, and to run our functions, what I'm going to be doing is I'm going to set all my functions to run on our tutorial endpoint, which is an endpoint that we as the Globus Compute team run on Amazon services. So this endpoint basically goes to that. This endpoint is one of the very few public endpoints where anybody can send functions to it. So it's a very small sandbox environment where you can run small functions. The next bit that I want to show you is I'm going to be basically pulling out the credentials from the session, like I mentioned earlier. And here's what I'm going to be doing. The important bit is this. The executor that I imported, like the Globus Compute executor, is going to be instantiated with the endpoint ID set to the tutorial endpoint to create the Globus Compute executor. So the executor is now created. And to begin with, you have to always run the hello world function. So what I'm going to be doing is defining a hello world function. All it does is just runs this little function which returns hello world as a string. And I'm going to submit the hello world function to the Globus Compute executor. So I'm going to say gcu.submit, and it is going to give you a future back. So as the print statement shows you, the submit returned a future, and it says right here that the state is pending. Now you've got two ways to interact with this, like I mentioned in the slides earlier. One is the non-blocking way of poking at what is happening with the function, which is feature.done. So now it says feature.done is true, meaning while talking, the function actually then got dispatched to Globus Compute. The compute services dispatched it to the endpoint, executed it, and the result came back already. And if I say feature.result, I will get hello world. Now, what I want to show you is what happens if I run this function and immediately ask for feature.done. And the answer is I get false because compute hasn't had a chance to execute it yet. I can poke it again, and there is a very good chance that because it's such a tiny function, it's already executed and the feature has updated its state to its done state. Now again, you get feature.result is hello world. Now, as you might know, if you have done anything in a distributed environment, what you're going to run into pretty often is exceptions and failures. And Globus Compute makes it very easy to actually get at what exactly failed on the remote side. And since we are presenting this Pythonic interface, the primary way by which you get exceptions and errors remotely is the exception traceback. So here, what I'm going to do is I'm going to have this little function which just does the obvious divide by 0, which would raise a 0 division error. And what I'm going to do is I'm going to submit this function. When submitting this function, we're going to wait for it and see what comes up. Now, what happens is this print statement triggers. It says Globus Compute returned an exception, And what you got back is this traceback, which says division by 0, 0 division by 0. Now, I want to make sure it's this. It's taking a little bit longer. Oh, it's not the context. Missed bracket. Yeah, so this is the bit that I wanted to show you. Now, remember that the function which would raise the zero division error came back with the exception. Now, while we do bring back the traceback, the exception that we bring back is not of type zero division error. This is there to make sure that even though your function that is running remotely might raise something like an error from an exotic library, like say PyTorch, and say you don't have PyTorch in your client, we would be serializing and bringing back a string dump of the exception so that this exception can always be deserialized. Because if you bring back an exception and you cannot deserialize the exception, well, then you cannot see what happened remotely. So this is a workaround to make sure that you get to see what exactly happened remotely. The next bit that I want to show you is how do we deal with functions with different arguments. So here, what we have got is a very simple function, getSum. It takes two integers, adds them up, and returns the sum. So here I'm going to say gcu.submit getSum, and I'm going to give it two numbers. So under the covers, what is really happening is the Globus compute executor is taking the function, its arguments, serializing them, and shipping it to the remote endpoint for execution. Now, all of the serializing is happening under the covers with Del, which is a Python library. And the bit that I want to point out is that here, the execution and the arguments that were supplied for this function are pretty simple because it's just two integers. But could it be any arbitrary argument to it? And the answer is there are some limitations. First of all, these arguments need to be serializable. Now, there are some known limitations with serializing objects in Python. But the first thing that I want to mention is that if your data objects are larger than 10 MB, Globus Compute will reject your functions because it's too large for our pipes. The second thing that I want to mention is that some functions simply do not serialize. So there are some exotic functions that hold state. There are some arguments that hold state. For example, if you try to ship a future itself, that is illegal because a future contains a mutex lock. So you cannot ship a lock, for example. So just be wary of the fact that while most data structures can be serialized, there are some limitations where certain data structures simply cannot be serialized, and you might have to look into alternative solutions for getting that working. Do we have a question? Can you submit a function, come back later and call it with arguments? I'm not sure I get that.
I assume he's referring to registering a function, what we call registering. So yeah, assuming that's what you mean, yes.
Yes, you can register a function, get a function ID, and submit that function multiple times later. That is a working pattern.
Yadu, should we
like the calling of the function is a task. Sorry,
Yadu, do you want to show an example of how that works?
With the SDK? Yeah.
Is there an example in here? Can't remember.
There is no example here because this is basically all the executor-based examples where the assumption is that. Yeah, I could show that. Let me just do that right now. So what you want to be doing is something like this.
I just really want to see Yadu thinking on the fly.
I got that.
I also
So,
kind of cover this in the endpoint section because I cover allowed functions on the endpoint. But yeah, you can do it here.
Okay, so first of all, when you run into questions, the most important thing is go to the compute, read the docs. I should have covered this in the beginning because this is what you need to be doing. So you will actually see this. So this is already introduced here. Like there is the client is instantiated here in the tutorial itself, and the client is what is passed to the executor because this is just how we are doing the auth. So I'm not going to skip that because the Globus compute is the client is already here. So I just want to show you that the client is here. So that's what I'm going to be interacting with. So there is the Globus compute client.
So Yadu, you can actually, the executor now has a method on it to register functions and submit to registered functions. So if you wanted to do that as well, that's gc.register function.
Well, let's see how that goes.
It'll return the function ID. Yeah.
Oh, the function is already registered. Oh man, let me just create something else.
Create a new executor.
Yeah, let me show you another important bit as well. So when you write a function, make sure that it is also fully self-contained and pure, which means you only act on the inputs. There's no pure stateful behavior. And you also import all the libraries that you need inside it. Let's leave for a tiny second. And what happened? Oh, did I cause the executor to crash? Let me just restart this.
Yeah, you can just reinstantiate the executor. That's fine too.
Yeah, I'm just going to restart the command.
So in hindsight, I shouldn't have encouraged you to go off script, should I?
Well, this is what happens, but that's the fun part.
What point's a tutorial if it's just autopilot canned stuff? This is the real tutorial.
The real tutorial, right?
Get to see Yadu doing strange things.
Oh, sure. I did add a. Just want to make sure that. Okay, so I ran the. Wait, what? Did that complete? Huh. That didn't print anything. Wait a second, what is going on here? Okay. Oh, cool. Yeah. So I registered the slow hello world function, and I got a function ID back. And now the interesting question is, I've registered this function. How do I run this? And okay, yeah.
So it's
run endpoint.
It's submit to registered function from the executor. So just, I guess for everyone's clarity, formally a client object is something that's used within the executor, and that formally was sort of, were considered sort of like super user functions. The executor is the recommended route to actually submit tasks. So we sort of added these helper functions here because people were more commonly using them.
Oh, is it function ID? This is going to be interesting. We'll see what happens. Oh, that came back. And guess what? It went and slept for 0.1 seconds and came back with hello world, as you would expect. Now, what I want to do, oh, actually, do we have time for other things or should I get to the end? Do we have any other questions?
Yeah, we got some buffer, so you can just continue. with this back on. Do you want to?
Okay, I'll come back once I get to the end, just because I want to make sure that I cover all the important bits. Okay, so like I said earlier here, I showed you the slow hello world, which sleeps for a little bit. The important bit is that that is a function that has a dependency, right? It actually requires a library to be imported for it to actually do the functionality. So if you have a function, for example, that acts on some data structure and you need to use, say, NumPy or some other library, make sure to import it inside the function itself so that the methods that you use are actually available inside. Do not assume that if you specify something like import date, that import is going to actually reflect in the remote environment. So here is this example where it's basically doing what we did earlier with slow hello world, which is you import a library and you act on a method, and here's what would happen. It would just run remotely, import that library and run it and bring you back the result. So now the last bit that I want to show you here is some of the more interesting options where you want to go outside of Python. So let's say you have a function that you want to execute remotely, but what you really want the function to do is run some molecular dynamics application like LAMPS, or you want to invoke your genome sequencing pipeline remotely on the target supercomputer cluster. So here's one of the ways to do this. What you could do is, because you are in Python land and you have the full functionality of the Python language behind you, you could very well just say input operating system, os.popen and run the function. So this will work. But we've got something new, which allows you to do this in a slightly easier way. And I want to show you how that works. So the first bit that I want to show you is SDK. So it's 2.14, but we are well past that at this point, and this notebook has not been updated recently. So what we want to be doing is updating the environment that the notebook is running in so that we have the latest compute SDK to get this new functionality. And the new functionality is called shell functions. And it's a simple abstraction to allow you to encapsulate a command line execution that you want to just run remotely and hand it over to compute for execution. So how you would do is go something like this. First, I want to do a install. Also, if anybody has questions along the way, please ask.
Yeah, this is another another area we're going off script. This is pretty new functionality that's been integrated in the last month or so. So we haven't got this into the notebook and the docs. Goes alongside some new functionality where you can run MPI apps as well in a similar way that Yadu can speak to, but we're not going to do an example of that today. That felt too far removed from things we'd polished.
Yeah, that's true. So again, we are still showing 2.14, and what we need to do is restart the kernel so that the Python environment will reflect the package that we just installed into it. So now that we've done that, let me redo the activation. What's going on? Open ID. Kyle, I think I might have broken something. Ooh, what is this? You know what? I don't need any of this stuff.
Yeah, I don't see why that would break, Yadu. I think that should just be
Yeah, I know. But what this will do is, so unlike the previous rounds of iteration through this notebook, where we were picking up the Globus compute credentials from the session, the environment itself, this would ask me for authentication. And I can do that. It's a bit of a nuisance. So now I've authenticated. I can get back to stuff. So this would work. I run that. I get, I can run the stuff like usual. Just wait a second for it to complete. Yep. So as usual, I'm registered, I'm logged in, and I'm able to run functions. And as we get to the bottom of this, towards the end of this notebook, what we see here is this little snippet where we've imported the Globus Compute SDK to get the version info. And the version now shows us 2.28 instead of 2.14. And that means that we've got all of the new functionality. So run Globus Compute SDK shell function. So execute that. And just like the example above where I'm saying echo hello from hostname, I want to write a new style shell function, which will get you the same thing. So what I would say here is echo hello. I'm going to say my name, hello name from $hostname. This is what I want to execute remotely. So, and how I would run this, like this. And I'm going to give my name as hello, Yadu. This would return a future back to me. And this is what I want to show you. I got this out and so the shell function is simply essentially this. It's an abstraction that we have provided. It's syntactic candy. It basically gives you the mechanism by which you could give it a string. It would execute that string remotely and give you a lot of extra functionality on the execution. For example, it would automatically capture std out, std from the remote side and bring it back so that when you run your functions remotely, it guarantees that we have enough debuggability. So the result of executing a shell function is a shell result. So you could very well just do this as well. Yeah, so it would execute this remote locally, but instead we have submitted it to the remote endpoint for execution, and it brings you back a shell result. Now, what is inside a shell result? And so the shell result by default will bring you back exit code, I think. Oh, sorry, it's shell result. Sorry, this is going off script and it's mixing up names. STD out. So it would bring you back the STDR from the remote side. So it ran on the remote machine, and apparently the name of the machine is 562 something something. So it brought you back that, and it also automatically captures STD. So in this case, what it says is, oh, task sandboxing will not work due to endpoint misconfiguration. Basically, this is coming from the fact that the endpoint that I'm running this on, which is a tutorial endpoint, is not set up to automatically sandbox tasks into its own little sandbox directories. once you enable that, actually this warning will go away. Every function will run in its own sandbox directory by default when that is enabled. Now, we've seen so many different ways of running little tiny functions, different variations of it, functions with arguments, functions with import libraries. But now I want to show you basically what would happen if you want to run a bunch of functions in one go, because that's really where compute is really powerful. So what I've done here in this tutorial is basically the Monte Carlo method for calculating pi, which is you throw a bunch of darts at a square and find what fell inside a circle and use that to compute pi. So what we're doing here is, again, write a little pi function. It tells it how many points to take and how many points to drop. And we import the random package. And once we do that, we calculate what number of points fell inside the box. So what we are doing then is do this estimation by appending all of these results and averaging them. So here we go. All we're doing really here is this. We basically run a bunch of these invocations of the pi function. You submit the pi functions, wait for the features here. So that's what is happening here. So you submit a bunch of the pi functions, get all the features, and wait for all of the features here in this list comprehension. And once you've gotten all of the results, what you do is you average them right here. Right. And again, one last bit is you can use, sorry, I didn't define the GC because I messed it up when I threw away all of the session setup stuff. Oops, I cannot show you how this works. But I think that is pretty much everything that I wanted to cover. Does anybody have questions at this point?
Thank you, Yadu. So I guess one key point there, I don't know, I went to grab my lunch real quick at the beginning of that. One key point is that anyone can run that tutorial just with the link. So Yadu, if you want to pop the link in the chat here, you can run that. You don't need to install anything locally, no Docker containers, no nothing. You can just run through everything that Yadu did by shift enter, shift enter, shift enter, and you'll feel like you ran the entire tutorial. And the lesson is don't go too far off script. So Reed, we have 10 minutes left before the break. Do you think you want to give a summary? No,
I went so far off.
I was equally over time, and then I also derailed your presentation. So Reed, do you want to maybe give the intro to single user endpoints? Then after the break, we can come back and try them.
Yeah, I can just see how far I get too.
Yeah, okay.
You want to do that? Yeah.
Again, sorry, Reed.
That's all good.
Anyone that wants to try this out, probably Docker is your best bet, or SSH into a system to which you have access. Is that right, Reed?
Yeah, I'm actually going to go through that real quickly.
Okay, right. Of course you are.
So, all right. So yeah, I'm Reed Mello. I'll cover endpoints, and the first type of endpoint I'll cover is single user endpoints, and that's a bit of what Yadu had already discussed. So first thing, like Yadu already discussed, we pip install the Globus compute endpoint. So I'm just going to set up our environment here. Is this text too small for you guys? Would you like it bigger?
I think it would be better, slightly bigger.
Slightly bigger. Like that, maybe?
Yeah, that's good.
That's good.
Okay, cool. All right, so on the right here, I'm going to run the endpoint. On the left, I'll run the SDK just so for you guys to know what's going on here. So I'm just going to pull down, you guys can, if you're following along, you can use really any kind of Docker image you want here. I'm going to use Python 3.9. This is a little important when we get to the multi-user endpoint stuff, because I want to make sure that my environments are the same on both sides. I'm also running Python 3.9 with my SDK. And then in our current agent version utilizes 3.9 under the hood. So recommend doing that. If you're on Mac like I am, probably specify the platform here. This is not going to matter for single user, but it will matter for multi-user when I do later. And yeah, so I'm just going to launch this Docker container here. And let's see, I will create a Python virtual environment. Actually, first thing, so single user endpoints typically run in a non-privileged user. So let me just add user account here. And get to me. Okay, and I'm going to create a virtual environment. I'll just call it then the SDK. Activate it, and I will install Globus compute endpoint. So this is this part of the slide here. The next step, once that's installed, I'm going to configure an endpoint. That's going to output a config file here, which I'll show you. It's a default config file. Once this is done installing, I will run Globus compute endpoint configure. So configuring is just sort of setting it up locally. At this point, we don't actually register anything with the web services. So I'm going to call this RSE endpoint to match my slides. Again, it'll tell me where the configuration file exists. So it's going to be in my home directory. We'll create a .globus compute directory, and I will have then the endpoint directory and then config YAML. So actually going to, I need Vim here. Yeah, let me install this real quick. Apt install app update. Vim. I think that's all I need. So I'm just bouncing back to root because I didn't give my user sudo privileges. Okay, so I'm going to edit. Let's see here. Where am I? Let's go to my home directory, and I'm going to edit the configuration file here just to kind of show you guys. So this is the default configuration that will be run. I'm going to go into this in a second on what this means, but it's just good to know that this is essentially the file that's being created here. Okay, so next step, we're going to start the endpoint. So I will do Globus compute endpoint start RSE.endpoint is what I believe I called it. So same thing we saw before, I'll have to run this login flow here. I'll grab my token and paste it here. You can also do, you can run this with client credentials. So that's part of our sort of general Globus platform. You can get a client ID in secret and run this to automate. So the endpoint is running, and if I run Globus compute endpoint list, oops, it's a typo. I can see my list of endpoints running. So I see that I have RSE endpoint running, and I have the endpoint ID, which I will use in a moment. Okay, so that gets us through the kind of initial configuration and starting of the endpoint. Next here, we're configuring a single user endpoint. So I already kind of covered the default configuration here. This was from a previous slide here. We were presenting this at PERC, but you can set things like the AMQP port that's used. So a common scenario is people want to use 443 rather than the default AMQP port. You can set the display name. There's a bunch of configuration options that can be configured here. I will defer to the docs on most of that, but some simple things, because this is the default configuration, we're not behind a scheduler in the cloud or anything. I have a local provider, which is basically the way that I'm accessing whatever resource I'm on, and the engine, which is another concept here. So yeah, this is a very basic sort of single user endpoint. A question that came about earlier is how to handle different environments. So a couple different ways to do this. A very common way is that you utilize this provider configuration variable called worker init, and essentially you can define any script that you want here to run when the worker or just before the worker is starting. So a common use case is to activate a Conda environment. But yeah, you can activate Python virtual environment, et cetera. And the dependencies that your function will call, even if it's imported within the function, need to exist in the environment that you're initiating. Another use case here is to use containers. So we do support containers. In this example here, I'm specifying the container type Docker. I'm specifying the container URI, and then some command options that I can add to the launch command. So yeah, this basically will launch the workers within this container environment and utilize whatever dependencies exist in that container. That's a high level of environments. We can cover some scaling things here. So there's a number of different knobs that you can turn to adjust how the endpoint scales. So in this case, something simple is that whatever, depending on whether you're using an HPC or cloud, you're going to have some concept of a node being returned, and you can set your max workers per node. So I think by default, we set this to 1, but you could, for example, here, set this to 8. And if you're submitting a bunch of parallel functions, you'll be able to utilize 8 workers. Yeah, I think, how am I for time here? Keep going. Yeah, okay, cool.
3 minutes.
Nice. Here is some example of how to use a batch provider or a batch scheduler provider. So for example, here, if I'm running on Expanse, it uses Slurm. So I'm going to use the Slurm provider here. I can set a number of different configuration options here. Again, I'll defer to the documentation or maybe questions later for some specifics here. But I'm specifying the partition. I would specify my account, any kind of scheduler options, the worker in it, like we discussed before, wall time, etc. There's this concept of block here, which again, we can get into this more later, but a block is really an abstraction for a allocation request. So if that's in the cloud, that's likely an API request with a single node return. If it's for, an HPC, this is going to be some sort of batch of nodes that are getting returned. So it's sort of like an abstraction layer between, that sort of deals with the any kind of request you're making for an allocation. So yeah, this is some more examples here. So we're setting, for example, the number of nodes per block, and then we have the workers per node. So if you can think of this as sort of a hierarchy here. So the block is the kind of the most granular level that you can think of a request to a specific resource. So we have 8 nodes per block, and then those nodes will then launch 8 workers per node. These configuration variables here are doing things like init blocks is just immediately, without even sending a function, we're going to initialize a certain number of blocks. So we're going to make that many requests, in this case 1 allocation request, and then we can set a minimum and max number of blocks. Debugging the compute endpoint. So we have this command here. So there's a number of different ways to debug, but a really good way to get a single sort of packaging of all of the logs and a bunch of other information about the system. This is very commonly what Globus support will ask you if you open up a support ticket to submit over to us. So you can run Globus compute endpoint self-diagnostic, and with the -z flag, you'll get a gzipped file of a whole bunch of different things. You can also just look directly in the logs within the endpoint directory here. So I think I don't have a section in single user in my slides to actually run a function, but I am going to do one here while I have, it looks like I'm right at time, but I'll just do one really quickly. So let's just run this, and I'm just going to, so I already have installed Globus Compute SDK within this virtual environment here, and I'm going to import the executor. I'm not going to use the Jupyter notebook like Yadu just was to avoid some of those issues. I think this will just simplify things. There we go, and I'm going to specify the executor and get my endpoint ID, which I have here. So I'm just going to copy this endpoint ID and specify it here. And I'll specify a very simple function. Okay, and same as Yadu just covered, I will submit the function. It's still pending, so I will do a blocking call here until it returns. And there you go. So there's your function running on an endpoint I just set up. If I wanted to get that diagnostic logs here, I could run Globus compute endpoint self-diagnostic -z. And even if the endpoint is running, I'll be able to get the output here. And I can do gzip. I don't have less. So you get a bunch of useful information here. You can use this for your own debugging, but you can also, this is going to be definitely something that we request when asking. So you're going to get all your dependencies, and we do a number of tests out to the web service, etc. I'll let you guys dig through that. Okay, probably at time now. So I think let's see if, the next section is going to cover multi-user endpoints, which is a lot more in depth. And then we'll take some questions after that.
Yeah, okay. So everyone has a 30-minute break now. So we'll see you back at, what was it, 1 hour behind? So 1 p.m. Mountain Time, potentially, assuming I got that right. Have a good break. Enjoy your lunch, dinner, whatever time zone it is. And we'll see you in 30 minutes.
Alrighty. So as promised, I will go over multi-user endpoints now. So, and actually, I should probably just explain, I think I didn't cover this probably sufficiently because I was rushing in the single user. So single user endpoints, only the creator of the endpoint, the person registering the endpoint, can actually submit tasks to that endpoint. We have, there's a number of our kind of early adopters that we've utilized a methodology to kind of basically add people within a Globus group after they get permission from the endpoint administrators, et cetera. But this was really just a sort of a hacky way to handle multi-user endpoints, which we now have official support for, and I'm going to go into those in a second. So multi-user endpoints are endpoints that are typically deployed as a privileged user, so as root or any other kind of privileged user that can drop privileges. And yeah, I'll go into the details of this in a second. So first we'll go over the value add for users. So a common scenario is that users were, if you had a number of different endpoints that had different configurations, maybe a different account on the scheduler, different scaling configurations, et cetera, you would have to manage a bunch of different single user endpoints. So this kind of turns into an administrative nightmare if you have a lot of these. So with multi-user, you have a single multi-user endpoint that you deploy, and as I'll get into, you can have many different configurations, and these configurations are actually specified at task submission. This then means that there's no need to log into the target computer. So typically an endpoint admin will set up the multi-user endpoint. They will create a template, as I'll go in, that the users can send variables to, and the actual users just have to submit their functions and specify the configuration knobs that the admin has set for them and wait for results back. They don't need to actually log in. So value add for administrators. So for the reasons I just went over and some that I'll cover, there's a lower barrier for users. It gives a templatable user endpoint configuration, which gives the admin control. So again, I'm going to go into that in a little bit. So actually some examples of that would be, for example, the admin might pre-choose the provider, so Slurm or PBS provider, for example. So they don't want the user to be able to change that. They might set certain limits on scaling configuration, but then maybe they allow the user to specify their account or some other kind of variable. There's no orphaned user compute endpoints, so there's an enforced process tree. So when you shut down the multi-user endpoint, all of the what we call user-specific endpoints, all those processes are shut down with the multi-user endpoint. So as I just said, idle endpoints are shut down per endpoint configuration as well. So even if you don't shut down the multi-user endpoint, the endpoints that are launched in user space, the isolated endpoints, will all shut down based on some configurable timeout. And we use the standard Globus identity mapping in order to drop privileges. So again, I'll go into that in a minute, but if any of you are familiar with GCS, you can actually utilize the same identity mapping files. So here's a high level of the architecture here. So see at the top, we have the Globus compute web services, and then at the bottom, I'll kind of go into some of the details there, but this would be a multi-user endpoint deployed at some allocation. So number one, we submit via the executor. So this is the SDK. So we provide the endpoint ID of the multi-user endpoint and then some user endpoint configuration. Let's submit that up to the web services. The web service then basically has some checking to see the status of that multi-user endpoint. If it's not online, it'll send it a start command. The start command includes the identity of the user that's submitting the task, and obviously, and then the some information about the what's called the user endpoint. So we submit this down to the multi-user endpoint. At this point, we do a number of things, including we fork exec the process. And we basically fork the process. We drop privileges. We resolve the template. We do identity mapping actually before that, and we then exec the process to launch the user endpoint. And this is all within user space. The user endpoint operates just like a single user endpoint that I just covered before. So it's going to launch nodes, etc. And at this point, it's then the user endpoint has a direct connection up to our web services to pull down tasks and submit results. Yeah, I don't think there's much more to cover on that. So we'll get into multi-user installation. So just to clarify something slightly in what was said earlier, you actually can pip install multi-user endpoints. A much more common scenario is to use our RPM or Debian packages. So I'm going to kind of go over that here, but if you were following along previously in your Docker container, you already pip installed Globus Compute Endpoint, you can just utilize that. So I'm going to actually go over to our documentation so I can copy this code more easily. So if you go to our documentation into multi-user endpoints, you can see the deb and RPM installation instructions here. So there's some stuff I have to get here just for the sort of the Globus keys. And then I can install Globus Compute Agent. So here I haven't changed anything since I did the single user. So I'm going to deactivate this virtual environment and I'm going to go into root. And here I'm going to install the agent. So I'll do app update and apt install Globus Compute Agent. Okay, so I can see I have Globus Compute Endpoint here. If I do which, you'll see I'm installing it in user sbin. And if I run Globus Compute Endpoint list, because I'm now running as root, we have access to a different series of endpoints. I'm going to see that no endpoints are configured. So let's go back here. The next step is to configure a multi-user endpoint. So same process as the single user, except I'm going to specify the -- multi-user flag. This is going to create the standard endpoint configuration file, but then it's going to create a bunch of other files that are specific to multi-user. One is I'm going to go over all of these in a bit, but we have the identity mapping file. This is where we take your Globus identity and map to a local user account in which we can drop privileges. We have the configuration template. So this is it's a Jinja template that the admin specifies, and this gives the variables that can be specified at task submission by the user. Configuration schema. So this is a JSON schema that applies to the user configuration variables that are sent up. So this is an optional. You don't have to build out a schema here, but it's fairly common for admins to want to have that additional control so they can add some kind of type validation or number of other things. And then environment variables, which is a place we can define environment variables for the endpoint environment. So let's go back to here. And I'm going to do configure RSEMU, name this whatever you'd like, and I'll add the multi-user flag here. So like I said before, it's creating all of these different files. And just make sure root here. And if I do Globus Compute Endpoint list, I'm going to see I have an initialized endpoint that's not running yet. Actually, I guess I'll start it on this slide. So let's attempt to start this up. I should be able to start this right off the bat. It's going to use the standard config template will use local provider, et cetera. So I should be able to start this. And I have to go through this again. And again, the reason is I changed user space here. I'm in root, so I store my tokens in in the roots Globus compute directory. So there we go. I start the multi-user endpoint. We attach this to the terminal process, so that's why it's a little bit different here. I can't then run Globus compute list to see. I mean, I could start another terminal session here, but I think you guys get the point. So the multi-user endpoint is started here. I'm going to take this endpoint ID, and I'm going to go over to my SDK on the left here. So same thing as before. I haven't changed this, so this is my old endpoint ID. I want to now change this to my new endpoint ID. So something you can do here, you can specify the endpoint ID in the executor during initialization of the executor object, or you can just specify it here. So as an attribute, I will do that. And let's go to the next step here. Okay, so if I start my multi-user endpoint and I attempt to submit a basic function, I'm going to get an error. And the reason is I'm attempting to do identity mapping, but I have not configured the identity mapping file yet. So we have an example identity mapping file that's created automatically, but it maps. It has a mapping that's essentially not going to work for anyone. So you'll get this error return, which I suppose I could show here. So let me just submit this. Submit. Yeah, so there's the error. So in order to do that, I'm going to stop my multi-user endpoint. And I will edit Globus compute, RSE'24, and I can see the different files here. I'm going to, in this case, edit the example identity mapping config. I can change the name of this file. I can put it in a different location. I could utilize the identity mapping file I might already be using with GCS. I would just have to basically specify the path in the multi-user endpoint config. So if you guys have questions on that later, I can show you. But here, I'm going to edit this file. Let me space this out a little bit. So as you can see here, I won't going to go into all the details of what identity mapping file is. I'll defer to the GCS documentation for this. But at a high level, you have a list of mappings here. This is being applied to your identity list that's sent down from Globus. So what we're doing here is we're looking in the username field, which is going to be like essentially the email you're using to log in with Globus. And we're going to, in this case, we're grabbing, assuming you had an email at example.com, hence why this is not actually working. We would grab your email username here and then utilize that as your local user account, right? So this is a common scenario that people will do. So in our case, I'm going to change mine to uchicago.edu. And my username is Armello, which I already set up as my local user account. So this should now map to my local user account. Another thing just to mention with identity mapping is you can utilize a script. So you can really do as complex identity mapping as you want. Again, if you're not familiar with GCS, I suggest that you go take a look at that documentation. They go into good detail there. But yeah, you can do really complex mappings here, and a lot of our customers do just that. So I will save that. And now if I am to submit, I have to instantiate a new executor. And I have to start my endpoint. Start RSE-MU. Okay, actually, I should go back to my slide. So, yeah, my slide basically shows this. So I have to update the identity mapping file. I have the link here if you guys are interested for the GCS identity mapping info. So yeah, this just shows that it's at the example identity mapping config JSON, and I update this to uchicago.edu. So now if I were to start my multi-user endpoint, submit my function, it should work. So we can try that out. Again, I've already started it. I've updated the identity mapping file. I have my executor here with the correct endpoint ID. So now I will submit. And call f.result. So typically when you're submitting to a multi-user endpoint, the first task is going to take a second because it has to, basically start up the user endpoint process and do a few other things. But after that, I should be able to get a result immediately back. So it's very quickly returning. It's just the sort of initial, essentially anytime your user endpoint on the other side that's running in user space has gone down or idled out, then you're going to take a few seconds to get that first task back. But after that, it'll just be like submitting to a single user endpoint. You notice I have a little warning up here. This is just a warning. This is not going to stop, but basically there's typically, this is getting back to what Yadu was mentioning before with serialization across Python versions. So we essentially give a warning here. There's no issue because I am running 3.9 on both sides. Even if I wasn't running 3.9 on both sides, this is maybe not something that we should be endorsing explicitly, but most of the time that will work. There just is absolutely known serialization issues between Python versions. So, you wouldn't normally want to be running 3.11 on one side, on your SDK, and then 3.9 on your endpoint. But micro versions won't be an issue here. We do call it out because we look at this as like a heuristic to say that there is an environment difference. So we want to just call that out to make sure that the user is aware that we are detecting some environment difference here. So anyways, that's that part. So it did work. So let's get into the kind of bread and butter of multi-user. So that's the multi-user configuration or user configuration templates. So you see here, we have the user config template.yaml.jinja, J2. So
Reed, just quickly to interrupt here. Sorry to interrupt. But the one thing that I think we want to stress here is that multi-user might not be as well named as it could be. So the part that Reed's about to present now is really quite useful for a single user deployment as well. So you can deploy the multi-user environment with a single user account where it can't fork a new process in a different user domain or a user account. But what it can do is it can do all of the stuff that Reed's about to talk to, which is shaping the resources, provisioning on the fly via our APIs, resources to run your tasks on. Sorry, Reed, back to you.
No worries. No, that's perfect. Yeah, because I don't have a slide on that actually. Because just to clarify slightly, if you deploy the multi-user endpoint as a privileged user, anyone, basically you set up your identity mapping, or you can also do authentication policies, which I'll cover a second. And so that's sort of restricting access to the endpoint. But anyone that you allow to submit functions, you can have any number of users, right? As long as you're mapping to some local user account, they can submit functions. It'll be isolated in whatever local user account that you're mapping to. If you start a multi-user endpoint as a non-privileged user, it'll essentially operate as a single user endpoint. So only the person who registered the endpoint can submit functions to it. But again, you'll be able to utilize all of these kind of features like templating your configuration and whatnot. Eventually, I'm probably getting ahead of myself a little bit. Eventually, we're going to collapse these concepts. So it's a little confusing right now since we're still in transition, but you'll just be an endpoint that you either, or at least this is where I believe we're heading. It'll just be an endpoint that you either deploy as a privileged or a non-privileged user. And, that there's the different use cases sort of right off the bat, and the different behavior will be defined on how you deploy it. So yeah, anyways, we have the template here. So what I've done, if I were an admin here, I'm saying that the provider must be a Slurm provider, must use a CPU partition. I've specified the engine type here, the launcher, but I've given these variables here that I want the user to be able to define. I have account ID and wall time. Since this is a Jinja template, I can do any kind of Jinja logic, including things like, defining a default here, but I could have, conditional logic and a bunch of other things. And then on the user side, this is more or less what it would look like. I'm going to basically get my executor. I'll specify my user endpoint config. I have my account ID and wall time here, and then submit that. I will basically define this user endpoint config attribute and then submit the function. And on the other side, we'll launch a new user endpoint process within user space that applies the variables that I'm submitting up to this template. So I suppose I can do that out here. So let me cancel this multi-user endpoint. This will take a second because it's got to take down the child processes. Okay. So let's take a look at the template. So this is the default template here. We have a bunch of info on kind of what's going on. We set this up in a way that you don't actually have to submit any variables right off the bat, but I can take any of these and make them into template variables. So yeah, let's make max workers per node templatable. I'm going to create a oops. I'm just going to call it max workers. And I could edit the schema here. Let's see, might as well do it. Actually, I'll do that afterwards. So now let's start up the endpoint. And on this side, I'm going to now specify the user endpoint config. So it's just going to be a dictionary. Max workers. And in this case, I'll just say 2. So we have 2 workers. And now I should be able to submit. So although this is pointless, I'm deploying 2 workers to submit a single hello world function, but it just gets the point across. That'll take it a second again, because remember, like I said before, when you're first submitting your task, it's got to start the user endpoint function on the other side and submit back. And we get that warning again because, again, it's a brand new endpoint. So now if I were to submit functions, I get essentially immediate return. Okay, we'll move on. This is the schema. So again, yeah, I will maybe update one of these. So in this case, I'm applying a JSON schema to account ID and wall time. In this example, in my actual environment, I'll just change that max workers and I'll require an integer or something. I don't think I need to necessarily do here, but yeah, I guess I will. Let's see. Just stopping the endpoint. All right, so Globus compute endpoint, RSE, and we're going to get the user config schema. So again, we have a few variables here that we also are allowing additional properties here. So it's not really, this is essentially just going to work right out of the box. I'll say max. And actually in JSON schema, I believe I write out integer. Could be wrong there. What am I doing wrong here? I guess we're good. Okay, let's start this up. Something's wrong. I'm not exactly sure what I'm doing wrong here. Well, I'm not going to troubleshoot this right now. This is obviously just me mistyping something in the JSON schema.
I think you just wanted to remove that trailing comma.
Oh, is that all? Okay, let's try that then. Thank you for that.
Yep.
Yeah, that makes sense. There's our error. Thank you. Okay, so we started the multi-user endpoint. And just to give an example of this, I'm going to specify, let's do this. and I'll just put it in a string. Yeah, so get our response back, semantically invalid, request payload failed validation, unable to start endpoint process. So yeah, anyways, just giving an example here of what that looks like. And I have some, this is by default, certain types of logs will rise up here. Okay, so let's move on. Restricting functions. So here is a common use cases. People want to deploy an endpoint. They want a subset of functions that their users can submit to. And yeah, that's it. They want to block everything else. So we do support that. You can specify allowed functions. It's typically done in the multi-user endpoint config. So just a quick note too, as I said before, this is where the identity mapping config path is specified. So we have it by default, will automatically get populated wherever in the standard location for the example config, but you can change this. So yeah, here I can specify a allow list of functions here. And then I can submit a function using the specific ID. So in this case, I'm using the executor to register a function like Yadu did before. I get the function ID, and then I'm going to, instead of just using the executor.submit method, I'm going to use submit to registered function and specify the function ID. So let's give that a shot. So I'm going to make just a slightly different function here. Hello, safe world. Everyone knows that's a lie. Let's see. So I'm going to do FID equals register function. Because I had the error before. So we do this often. This is for a number of technical reasons internally to make sure that we're not, yeah, the executor is actually a whole series of threads that are doing a bunch of different things. So when there's errors like this, we often just kill the executor and we require you to reinstantiate it. So let's reinstantiate an executor here. Actually, just so in case I have to do this again. Okay. So there we go. I have my function ID. And now on this side, I'm going to change. So in this case, I'm just going to use config YAML, which is, again, the multi-user endpoint config. I will specify allowed functions and paste my function ID here. Okay, let's restart this up. Something is off there. Cannot resolve.
Is it because you created a brand new executor after you registered your function?
No, that won't matter. It's basically making sure that I have access to this function. That is strange.
Did you put in the right number? I think you might have used the endpoint ID, not the FID.
Oh, possibly.
Yeah, that looks exactly like what he's done.
Very
This is
possible.
good. Keep the audience on their toes, Reed.
Yeah, thank you
Got the
guys.
extra comma at
Yes,
the
you're
end.
absolutely right. That's
Use the
exactly what
wrong
I did.
ID. What's next?
Yeah. Oh, this is when you do live demos like this. I mean, okay. That looks more accurate. Thank you, guys. Okay, cool. So now, if I were to use the executor, I'm going to use submit to registered function, specify the function ID here. And then I believe after that, I then specify, oh, sorry, yeah. If there's any arguments after that for the function, you could specify them here. We're not really covering, and most of our examples are arguments here, but typically what you do is you have the function first, so in this case, the function ID, and then any number of args or quargs after. Oh, I have the max workers undefined here. So let's do, because I have a new executor. And also for speed here. Okay. Oh no. All right. Okay. Yikes. To do this, and then I should be able to submit. So, okay, that seems to be working now. So basically what I was just doing there is I just kept instantiate the executor, didn't have the user endpoint config defined. And then, yeah, basically have to make sure that that's defined. And then if you do that, then it's killing the executor and you have to reinstantiate and specify the endpoint ID. But in this case, I am able to submit that. If I were to register a different function, so I have the hello world function from before, for example. So if I just do CE register function, hello. Okay. Now if I do future equals GC submits to registered function, FID2. And yeah. I'm going to get an error back saying function not permitted. So again, very common use case, sort of around a long way to explain a simple function here, but it's just something to note as well. We enforce this both at the web service and locally on the endpoint. You know, in this case, this is just the web service submitting this back, but this is also enforced locally on the endpoint. So if for whatever reason our web service was bugging out and it allowed it to go all the way through, as an admin, you'd be able to see the code locally that's enforcing this. All right, and restricting access. Go ahead.
So how would you actually use that in practice? I mean, what I'm thinking is the situation where you have 20 users and they each have like 4 or 5 functions they need to call. So now you've got 100 functions you've got to allow. Do you just set up your 100 functions that you allow and run with it?
I can probably take this one, Reed. So the main place we see this used is when people are building portals. So like we have one example where there's some cosmologists and they've got a portal which allows analysis of data. And this is running at Argonne and Oak Ridge. And the administrators, the only way they will allow a set of other people to run or use this portal is by ensuring that the portal has a whitelisted set of functions that are allowed to be run. So the administrators of the Argon and Oak Ridge machine check the functions, they approve them, they're now whitelisted, and now users of the portal, who could be anyone, are able to run those tasks on behalf of the portal. So that's the main use case we see for that. I think if you were running a multi-user endpoint for all of your users on a machine, it doesn't seem particularly reasonable to be checking all of their function code that they're going to run, and currently you're not checking all of their function code that they're going to run.
Got it. Thank you.
Cool. All right, so next is restricting access. So that was obviously limiting the number of the functions that can be run on the endpoint, but here is just restricting access for who can access the endpoint, who can submit functions to it. So we have two different layers here. We have Cloud Enforce, which uses authentication policies. If you guys are familiar with other Globus, other parts of the Globus platform like transfer and with GCS, et cetera, you're probably familiar with authentication policies. I'll cover that a little bit, but basically the important part here is you can apply this to the endpoint, and the cloud gatekeeps submission to the endpoint. You can do things like domain restrictions. So similar to the identity mapping, I can say only people with a uchicago.edu account can actually submit here. We have some high assurance policies that you can set here, which is like basically ensuring that someone has logged in with a specific identity within a certain period of time. And we're adding a lot more to that. Then we also have endpoint enforced, and this is using identity mapping. So although identity mapping's main purpose is to map to a local user account that you can then drop privileges into, it sort of acts as a endpoint enforced access control as well. Because if you're only mapping users that have, in my case, the uchicago.edu email address, then anyone who doesn't have that will not map to a local user account, so their submission will just get rejected. So here we have some syntactic sugar here to actually create authentication policies with the endpoint CLI. So I won't go into all the details here. This is sort of just Globus concepts. We have a project in which you have to first create, which then can hold the authentication policies. We're specifying, in this case, globus.org is the domain, and then I'm so basically making sure the identity matches that. So if you guys are familiar with Globus Auth, you can have identity list. It's a big list of identities, and we'll look through all of those identities that are matched with each other, and we'll make sure that at least one of them matches this regex here. Subscription IDs, etc., which will unlock the HA feature. And you can edit these in the view the details and edit the policy details in the Globus web app. It kind of gives a nice interface there. And then you apply the authentication policy directly to the multi-user endpoint config. So similarly to how we did the allowed functions whitelist, we can apply the authentication policy in the same config. So I won't do an example here because it'll just take a while to set this up, but that's basically how you do it. Some more sort of syntactic sugar here is a common thing is you're going to want to create a systemd service. So we automatically will create the unit file for you if you run enable on boot subcommand. So I just say Globus compute endpoint enable on boot, and then specify the endpoint name, and we'll create a unit file that looks like this. Obviously, you can edit this all you want. We give some instructions. Obviously, you guys don't need this instructions, but to just enable the service, etc. And here is the web app. So you can see the endpoint that you deployed here. We have some, I think Kyle covered this earlier, we have some kind of basic statistics, but the important kind of part to the multi-user component here is that anyone who has access to this endpoint can come in here and see what the config schema is, so they can see what they actually need to specify when submitting a task. The template, which they can see the kind of the rest of the configuration that's predefined, and then the multi-user config. We're have tons of plans to expand this out pretty dramatically. So yeah, we can get into that if you guys are interested. Oops. And yeah, okay, any questions? I guess we should probably open it up to questions for any of the presentations.
Yeah, yes. Yeah, we can take any questions. Let me just share my next. I guess I'll share my whole screen now because I have to do some notebooky stuff. Okay. Can we see my screen? Start with this one.
Yep.
Okay, so final part of the tutorial, we're going to go through a more worked application example. So if you want to follow along at home on this one, the first step will be make sure you have Docker set up because we're going to load a, well, it doesn't need to be Docker. If you've got another system, you can set up a Conda environment. That would be just fine. But Docker is probably the easiest, and we provide a Docker file. Okay, so the example we're going to focus on, as I mentioned in the introduction, is to design new batteries. We're going to try and run a large parameter or a search sweep across a very large search space of potential molecules, looking for molecules that exhibit high ionization energy. So ionization energy is, as described here, is the amount of energy needed to remove the most loosely bound electron from an isolated atom, molecule, or positive ion in a gaseous state. So apparently, according to our material science friends, we want to try and search through a near limitless number of molecules for those that have very high ionization energy. So how do we go about doing this? Well, we can do this experimentally. That turns out to be very expensive. We can also do it with quantum chemistry simulations. This is significantly faster than doing it in a lab, but it's still actually computationally very expensive to run these things. We're talking using entire supercomputers for reasonably large-scale sweeps across potential molecules. So what we're going to do is we're going to look at a method of using machine learning to try and optimize this, this task. So again, our aim, identify molecules that have high ionization energy among a search space of billions of candidates. What we're going to do is we're going to set up a loop like this, where we start by simulating using what would normally be a fairly heavyweight simulation package. We're going to use a fairly light one configured to be as light as humanly possible because we'd like to actually run this workflow in a tutorial timescale. So we'll run maybe half a dozen simulations using this simulation package. We'll use the results that come from these simulations to train a machine learning model. We're just going to use a pretty simple model that's going to look at a k-nearest neighbors based on a fingerprint of the molecule, and it's basically going to use the intuition that molecules that are of similar shape in this this molecular space are going to exhibit similar properties. What we're going to do then is we're going to use this model to infer the ionization energy of all the other molecules in our search space. We're going to rank that list of molecules by those that have the highest, and we're going to take the top n of those inferred values, and we're going to run real simulations again. We're then going to put together all the simulations we've done, retrain the model, and keep going in a loop for several times. And hopefully at the end, we're going to see a set of molecules that have the highest ionization energy. Okay, so we have a Jupyter notebook to run through this example. Everything is available at this link here. In that, in this GitHub repository, there's a Docker file that we can build the Docker container. And so we'll start a Docker container where we'll deploy a Globus compute endpoint in that Docker container, and then we'll use our notebook running in our local laptop to basically run this molecular design workflow. Okay. Yadu or Reed, would you be able to pop this in the, I guess I can do it. Let me pop this in the chat. There we go. Okay, so first step, let's start. I don't have Reed's abilities here. So let's start with, okay. So I was just testing this. Okay, so here we are. I've just cloned this repo. Everything is here. You'll see here we have our notebook. And in here we have the Docker file. We have an environment.yaml, which has the Conda configuration. You see here we're going to set up Python. We're going to have Jupyter. We're going to install a bunch of specific applications, RDKit, XTB, which is going to run our lightweight simulation, some packages just to understand resource use, and the progress bar. We can basically create this by just Conda creating an environment with this environment YAML file to set it up. But easier is just to go to the Docker file. So let's start here. We can build the Docker file like this. we build. For me, it's going to be very, very quick because, of course, I already have downloaded all these layers. It's just running a few steps. We're going to start with let me just open this up. We're going to start with a mini Conda environment. We're going to update apt. We're going to create a test directory. We're going to clone the same GitHub repository we just had. We're going to create a new working directory, and then we're going to create the Conda environment, just using that environment.yaml file. When we start the thing, we'll start with bash so that we can actually interact with the container. Okay, so does anyone have any questions on that setup? I can't see the chat. But at this stage, if you're following along, you've hopefully cloned this repo, run docker build -t, give it a name, you can call it whatever you like, and dot, just meaning run the Docker file in this directory. It's been a while since I've run this. This might take a few minutes, just because it's a bit of an environment to solve with a few packages to install. Okay, so now we want to run this thing. So we'll do docker run. We don't need a shared directory. We're just going to run in an interactive mode our mold design Docker container, and we're just going to use bash so that we can jump in there and install the Globus compute endpoint software. Okay, so let's run this thing. I think I clicked enter. Maybe I didn't. I didn't. And here, you see here, this is the same repository that we had previously. Okay. Conda activate mold design, hopefully. I should just check that that is actually. Yes, so the name of the Conda environment is mold design. So I've just activated mold design. Oh. So we're now in this this mold design Conda environment. It doesn't actually have Globus compute, so we'll pip install that. Oh, I forgot one keyword. Install. Okay, maybe it did already have it given how quick that was. We'll configure an endpoint, which I didn't give it a name, so it's just going to be default. This is going to be set up with only a couple of, I don't know how many resources are allocated to my Docker container. How many cores are normally allocated to a Docker container? Does anyone know? No one knows. Yadu, where do I put max workers? Here?
Sorry, I was muted. Yes, right there.
Max workers per node.
Node, yes.
We'll set it to, what do you think is reasonable? 4.
2, 4, yeah.
I don't know how much my Docker container's got. We'll just
Yeah, probably put it to 2.
2? What?
2 is safer.
No, what's the worst that happens? Okay. And now we'll run this Globus compute endpoint. Worst case, if we're running 4 things and we've only got 2 cores, it's just going to be a little bit slower. Okay, let me quickly authenticate. I'll just trust whatever that is. Okay, so this is just our normal authentication process that we're now used to. So our endpoint started. This endpoint is started inside this Conda environment. So it has all the great stuff we installed in this mold design environment. So it has XTB, it has RDKit, it has everything else. In another window, so either from a Docker container or from your local environment, I actually just ran from my local environment. So I just had a Conda container here. Probably the easiest thing would be for you to run from another instance of this Docker container that doesn't contain the Globus compute endpoint, and start up the Jupyter notebook. So I'll just show you what I've done here. See, I've got this mold design demo. I did the same thing as I did on the other side. I just ran this environment file to create this Conda environment here, and then just started Jupyter. Okay, so let's open this up. Let me know if you're following along and you want me to slow down. Okay, we might as well make this, full size. How's that for visibility? Yeah, do a read.
Yeah, that's good.
Okay, one thing we probably want to do is quickly grab this endpoint ID. Let's pop this in here. Put it there. Okay. Okay, so what I did was I changed the default endpoint ID, which I have no idea what the default endpoint ID would have been, and changed it to the endpoint I just set up in my container. Okay, so as I said, we're going to try and implement this loop, this active learning loop, combining simulation, machine learning training, and inference, and do some cycles. Okay, we're going to install a bunch of packages that we need, matplotlib for producing the plot at the end that shows us we are doing a good job at what we say we'll do, pandas for manipulating the things that come back, concurrent futures.as completed. This is just a helpful helper method that allows us to wait for a set of futures to resolve. So as we said before, we are Globus compute executor implements the concurrent futures executor. We get all the future handling functions for free. Matplotlib as well here, and then some stuff for a notebook progress bar. Okay, so we're a normal scientist here. We've developed some code that's going to compute this ionization energy. It's called compute vertical, the vertical ionization energy. As input, it takes a SMILES string, and then under the hood, it runs XTB to run these quantum chemistry computations to give us back this measure of ionization energy. So we have a few functions defined here. We have this compute vertical function. Actually, I think I compressed this all into one. So yes, this was previously 3, but I just made it 1 for simplicity. So what it does, it uses RDKit, which is a pretty common library for interacting with molecules. We include XTB. We do some formatting here. So we basically take the SMILES string, which is like a string like O or C, O, C, 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 whatever, turns it into a molecule in this format, puts it in some space, and eventually here passes it to XTB. So we can run XTB by reading in this structure of the molecule, and out we get here an energy, which we can then use to convert into the charged energy and return that back to the user at the end. Okay, so this is a pretty simple piece of code using a bunch of external packages to come up with an estimate for a given molecule, what the ionization energy would be. If I was running this myself, what I would do is just call it. Okay, that shows you I didn't run this cell. I'm calling it here, passing it in O. O, oddly enough, is the SMILES for water. And what we get back is an ionization energy of 18.29 EV. I'm not sure if that's at all reasonable, but given at least I'm not a materials scientist and probably no one else is, I think we can run with it. So now what we want to do is we've got this nice computation. We want to run it somewhere else. So what do we do to do that? We import the Globus compute executor. We point it at our endpoint that we just created in our Docker container, and then we just submit it, getting a future back, and hopefully we'll get the same result. So let's run this. Okay, so we've submitted it. Now let's wait for the result. It's off there spinning. We are watching our notebook over here. Oh, it's too fast. It's already come back again. Okay, so you can see here we can run this pretty quick. It's up and running. It's probably going to give us a value that's pretty similar. I assume that looks pretty similar. 18.293366. 3366. I assume this would be somewhat stochastic. Oh, it is a little bit. The final numbers are a bit different, but looks like to about 10 decimal places we're about the same. It's remarkable. Okay. Okay, so that's pretty much sort of step 101. This is Globus Compute 101. We've taken this function representing real science. We've run it with Globus Compute using, 4 lines of code, create executor, run task with some input, get result back again. So the next thing we want to do is probably run a number of simulations. So we talked about having the search space, picking some values out of there, going and running them, and getting the results back again. So we've prepared here some sample data for you from QM9. You can see here, here's all the SMILES strings. You see, I told you the incomprehensible series of letters with bonds and atoms. I don't know how many we've got, but given the scroll bar on the right, it seems like we certainly have tens of thousands of them. See what happens. So we've got about 130,000 molecules. And what we'd like to do is get a good idea of that search space. Okay. So we're going to load this search space up into pandas by reading the CSV, just using a separator of a space, I think. Oh, yes. Here we can sample from that, or to speed up this tutorial, we can just pick 4 that we know are going to be pretty fast. So I've just picked 4 that I know are going to be pretty fast. It turns out the smaller the SMILES strings, the faster the simulation. So we'll start with 4 random ones that are not at all random. We'll go and create a list of all the futures. See, we're submitting here for each of these 4. Submit it. We'll add it to a list of futures. We're going to create a dictionary here that maps the future to the smiles that was actually submitted. And we're going to print that we've just submitted 4 calculations. So we'll submit that. Behind the scenes, Globus computer's off running these simulations, hopefully using the 4 cores I allocated in my Docker container, although unclear if I actually have 4 cores in my Docker container. And what we'll do now is we're going to wait for the results to come back again and collect them up and put them into a list of this format, a list of dictionaries where we have the smile string, the ionization energy, the batch, which we'll come to later, and the time, which we're going to try and record how long the time, what ionization energy we got at each time, so that we can hopefully see over iterations of our machine learning loop, our results are getting better. A couple of things to highlight here. So the first is we're going to iterate through here while we've got things in our list that haven't yet completed. We're going to use that concurrent futures as completed method that's going to look at that list and see if any of the futures have completed. When it's completed, we're going to take it out of the list. We're going to grab the smile strings, the smile string for the thing that ran. And then ideally, if it succeeded, we're just going to put it into our list of successfully completed application of runs. There's one big asterisk here. So when you're doing a lot of these types of science apps, there can be sort of some level of randomness in which the actual simulation doesn't complete. Some of these will never complete. Some of them are stochastic and they will complete if you rerun them again. For our case, we're just going to discard anything that doesn't run. So if this one failed, what we're going to do is we're going to say it failed. What we're going to do is we're going to pick a new smile string from our list at random of our 130,000, resubmit it, add it back to the list, and it's going to get caught in this loop. So let's try this. Given I picked 4 very simple ones, you see here they've all already resolved. All of them succeeded. These simple ones tend to succeed. So we didn't have any failures. But if we were running through that whole list and we had a more complicated one, we would see a failure here and we would have to skip it and do the next one. The failures can take a while as well. So ideally, we'd like to avoid them for right now, given we have a limited amount of time. Okay, so now we have this training data. So let's have a look at what that looks like. Train data, it's just going to be a list. You see, each of these smiles, we have some timestamps here, which all look very similar, which makes me think I do have 4 cores, which is a good thing. And we're seeing these ionization energies. So you see, of these, we got O, which we'd already computed, 18, CO a little bit worse, OC a little bit worse, C somewhere in between. And now what we're going to do is we're going to take this list and just put it in a data frame, just because this is what we're going to use for our machine learning algorithm. Okay, any questions at this stage? Take that as a no. Okay, so the next step, we've now shown, if we go back to our nice figure, we've shown we can do the blue bits. So we've gone and run a bunch of blue boxes, and now what we want to do is train this orange model before we use that for inference. So let's come down here. Where was that? Okay, we're going to train it to screen candidate models. So here what we're going to do is we're just going to train a very simple k-nearest neighbors model. We're just going to say 4. We're going to use 4 neighbors because we've started with 4 data points. We're going to use scikit-learn because it's nice and simple. We're going to define a simple metric, a distance metric, and we're going to fit this model to the training data we had above, where we're trying to predict, given this, what that's going to be. Okay, so given a smile string, what the IE will be. So let's run this thing. Well, let's first we define this function. And now what we're going to do is we're going to submit this off to our endpoint to train. So this is a really nice example, again, of what Globus Compute can do for you. If I had another supercomputer or system that was designed for training machine learning models, I would probably want to submit this training operation to that specific system. So I could change my endpoint here and run my training on the specific system I want to. I'm just passing in the model function, which is this, plus the data frame, which was this. And at the end of it, I'm going to get back a model. Takes a minute. It's chugging away on my under-resourced Docker container. I'm getting some warnings here saying I'm doing some dangerous things with different versions of scikit-learn. We're going to ignore that and carry on. Everything should be fine because I ran this earlier today. Okay, so now our model has been trained. We've got back our model. Let's have a look at our model here. That's our model, right? This is the thing that's come back again, is the scikit-learn object. So this is not something crazy, right? I've got the result out of the future. If I load it like this, I get the same scikit-learn interface I get in a Jupyter notebook. Now I want to run this thing. To run it, what I'm going to do is I'm going to say, here's the model, which is the thing I just got back. Here's the list of smiles I want to run inference on. Predict those values for me, okay? And give me back a data frame of, for a given smiles, what the predicted ionization energy is. So we'll run this, we'll define this thing. Now we're going to try and run it using O, water, as our input smiles. You would hope, right? So we're running model, we're passing in the model we trained before, and we're passing in a single smiles string to predict and give me back the value. You would hope that what it gives back is going to be pretty similar to what we computed from the simulation. Given it's a k-nearest neighbors, it should be a pretty good estimate. And so back here, we're getting, oh, we can change this. Let's do inference for C. See if that gives us anything like what C was before. C 16.94, this should be pretty similar, 16.94, right? What would be more complicated is if we gave it a value like, I don't know anything about smiles. Let's try COO and see if that's actually a smile string. So this is not one we've trained before. What we're getting back here, I don't know why we're getting it back 3 times. I don't know why we get it 3 times. Oh, maybe it's keeping it here. Unclear, but we're getting back COO. We're getting 3 values for COO that we haven't seen before. We'll need to look at that. Okay, so now what we might want to do, remember we have 130,000 things, 130,000 smiles we want to run. We have 4 cores maybe on our Docker container that we want to use. So ideally we want to make the most of that. So why don't we chunk up the search space into lots of smaller bits so we can run them in parallel. So this is some crazy list comprehension I wrote a while back that I can't understand for myself, but effectively it's going to chop it up into, I think, pieces of size 2036. We're then going to run a bunch of inferences. We're just doing a list comprehension here for each chunk in our list of chunks. Run it, get back a bunch of futures for each of those results. So if we do that, search space is not defined. Good start. Where is the search space defined? Yeah. I should have restarted this. Okay, so okay, so we've got that. Let's see how many inference futures we have. Okay, look, we got lots of them. Some of them are already finished. Look at how quick that is. So the first half of these have already finished on our 4 cores. Some of them are still waiting. Probably if we run this again, they'll now all be finished. So we've gone and run inference there for, I don't know what, 100 different, I guess we can see how many we had. 64 different chunks. The next thing we want to do is we'll just combine all these chunks together. So we'll take back all the results of each one of them. So we're going to get the result for each inference future and jam that together into a data frame such that we've got predictions for every single smiles string in our search space. So let's have a look at this. We'll sort by ascending value. So hopefully the highest is first. Funnily enough, of all of the ones we've got, O, which was the first thing we ran, actually gives us the highest ionization energy. This strange one from somewhere in the middle of the search space with a bunch of N's and C's and hash signs gives us the 3rd best value. Okay, so at this point in the, I probably should have actually picked a lower number than that. Too late. That's what we're going to do. The thing is, I've set this final. I was starting this final one because it's going to take a few minutes, and I was thinking, well, in advance, I thought I would change this number to search for fewer molecules just so it finished a bit quicker. But nevertheless, we're running with 16, and we'll hope for the best. So what I'm going to do now is just describe this model on the loop workflow. So at the moment, we're at this point. We've got the the Globus compute function that goes and runs the simulation. We've got the Globus compute function that goes and runs the model training, and we've got the Globus compute function that goes and runs the inference. What we want to do now is put this all together into a single application that's going to do all of that in one loop so that we can walk away and leave it running. So we're going to use a progress bar. So TQDM is just a very nice package that gives us a progress bar. You can see it down here. We're going to see progress as this proceeds. We're going to start the time so that we know, again, over time, we're going to be able to see the results come back. When you submit a function to an executor, is there a way to cancel that submission, or do you just need to wait for completion? This is an area that's under current active development. Reed, can you tell us the latest?
So you can't cancel it once it's actually been submitted up to the web service. I mean, there's technically the executor locally will batch the tasks that you're submitting them. So if you had a really fast loop and you canceled it really quickly, you could cancel it as long as it hasn't been submitted to the web service. But once it's there, yeah, it will get pulled down by the endpoint whenever the endpoint's online and attempted to be run.
Yeah, we're working
we're working on.
Yeah.
Go ahead, Kyle.
So, yeah, I was going to say we're working. I know I was in a meeting a couple of weeks ago where this was on the board to be developed. The ability basically to flush an endpoint, to cancel everything that's been sent to that endpoint, which will get rid of all the stuff in the web service and all the stuff that had even been pulled down to the actual endpoint to run.
Yeah, it's in the planning phase. And just to get some of the complexity there is like, canceling from the web service is one thing, but then there's obviously what happens when the task has been pulled down to the endpoint, what happens when it's already been submitted to the batch scheduler. And it's, there's quite a bit to make sure that we do this properly.
Okay, that's a great question, though. Thank you. Was Jason? Jason, thank you. Okay, I just quickly went down here to look at which molecules had been chosen, and I'm a little bit scared. Some of these are going to take a while. Okay, so let's go back to this loop. Hopefully, we'll get a few rounds through the loop by the time we're finished, and we can have a look at some of the results. Okay, so the first thing we're going to do, so this is basically taking all the code from above and just putting it together into a single function. So we're going to sample our search space and grab some number of samples. We're going to set that to our batch size. This is how many molecules we pick at each iteration of the loop before we retrain the machine learning model. We're going to submit them immediately. So we just go ahead and submit each of these smiles, right? We've got a for loop here for S and smiles. Submit it to Globus Compute to run the compute vertical function, give us back a list of futures. We're going to do the same thing before, create a dictionary that just maps futures to smiles so that we know what future belongs to which smiles. We could have put that as part of the result that comes back again, but there was a reason why that was complicated and this seemed easier. We're just going to print that. We're also going to set up a list or a set of all the things that have been run so that we don't need to revisit it. Okay, now we're in the loop that we talked about earlier. So this is going to be running through that loop, making sure we get 4 completed simulations. So we're going to use, again, the as completed function as part of concurrent futures. We're going to pass it the whole list of things that are currently running. Each time one finishes, this function is going to fill up this future, and then we're going to grab it here. So first thing we're going to do is we're going to take it off our list of things we're working on because it's finished. We're going to go and add it to our list of smiles futures. Oh no, here we're going to look up what the smile string was that belongs to that future. We're going to add it to the list of things that have already been run so that we don't need to run it again. And then the next thing we're going to do is we're going to check if it succeeded or if it failed. If it failed, as I said before, we'll just pick another one at random, add it to the list, submit it, add it to the list, and wait for that one to finish. If it succeeded, we're going to add it to our result data, and we're going to update our progress bar by 1 so that we can see we're making progress towards our goal of simulating 16 molecules. So we're going to do 4 rounds of 4, which certainly is not going to complete in the time allocated. Now what we're going to do, we've got to that point, we're going to get our training data frame, and we're going to go into a loop here that's going to do the ML training. So this is like the bootstrapping stage. In fact, we could have got rid of this bootstrapping phase completely and just used the 4 that we'd already run, which might have been a good idea given the time. But nevertheless, now we're going to go into the loop of the machine learning inference simulation. Okay, so what we're going to do is we're going to look for our training data to be as many as the search count. So remember, we wanted to find 16 full simulations. So we're going to say, while our training data is less than the 16 we're aiming for, keep running. First thing we're going to do is we're going to train a model, right? We're going to call the train model function by passing in the training data frame that we just constructed here. We're then going to chunk up the search space. You can almost think of this as so this is train the model. This is run the prediction. So we chunk up the search space of everything, submit all those futures, all the tasks to run, 64 of them. And then we're going to get back all of the results, combine them together into one set of predictions. We're going to sort the predictions, and then based on the sorted list, we're going to come up with the next set to choose, okay? So here we are. Now we've got a sorted list. We're going to go through that list in order. We're going to check first if it hasn't been run, because there's no point running a simulation twice for something that we've already simulated. We're going to grab the first thing off the list. We're going to submit it to the compute vertical function, add it to our list, add it to the list of the mapping, right, of the future to smile string, add it to the list of things that have run, print it, and then what is this doing? If it's greater than, so if it's greater than batch size, remember, we only want to do 4 things at a time. So if this is greater than 4, we've already got our 4 tasks lined up. Let's break out of this for loop, wait for these 4 to finish. So the next thing we're going to do is we're going to wait for every task in that batch to complete, and we're going to store the successful results. Here, we're not bothering with the results that failed. Importantly, of course, here, because it's a k nearest neighbors, I needed to have exactly 4 values. That's why here, if one failed, we needed to rerun it. Here, it doesn't matter if we rerun it because we've already got 4, so we should be good to go. So we're going to wait here for it to be completed. When it completes, we're going to update the progress bar, and then we're going to add the results to our list of results, and then carry on with the loop. So any results that come back, add it to our data frame, go back around again, train model, run inference, pick the top 4, run simulation. And that brings us to where we are on our progress. So we've 25% of our simulations have complete. We've trained now a new machine learning model. We've run inference for that new machine learning model, and we've come up with the next 4 of calculations to run. So you see these are not the same as these. So these were the 4 initial ones we ran. We've got the results for them. We're based on our model, we've decided these are the next 4 that we think are most likely to have good ionization energy. They're off running. They'll come back, I'm guessing, somewhere about 6 minutes from now. So based on this math, it's going to take us another 18 minutes to finish, which we don't have time for today. So what I'll do is instead show you one I ran previously, and you can see here over time. So this is the first 4 that ran. We got one with a good ionization energy. Then we ran another 4. We got one with a slightly higher ionization energy. We ran another 4. We got one with an even higher ionization energy. And then we ran another batch of 4. And these have relatively high ionization energy as well. So you can see the general trend here to be increasing, where the best molecule we're finding is getting better at every stage or every round. And also all the molecules we're testing are actually getting better as we progress over the various rounds. So with that, that's the end of the machine learning loop. Well, 31%. So we just had our 5th one succeed. With that, I will turn it over to questions from the audience. Apologies for not updating that to run fewer molecule calculations. How do I get back to this? Yeah. Okay, does anyone have any questions? Here's my participant list. Now I can see everyone. Okay, well, I can see Yadu. Question.
You've got an endpoint. Yeah, sorry. Suppose you've got an endpoint running on a machine with a GPU. What's the best way to take advantage of that?
Yeah, so that's a really common use case for us, because many of our endpoints are actually deployed on DOE machines that are all GPUs. So yeah, you can take advantage of a GPU exactly as you would with any other Python code. We have a bunch of support for like GPU affinity and things in the configurations that is described in the documentation. But sort of standard use, you'll just be able to run on a GPU with one of your functions the same way you would any other function that's running.
Thanks.
So Kyle, I'm kind of curious, not so much on the technical details. I'm curious on the funding model for all of this, because it looks like you guys have built an amazing tool, service, suite, whatever you want to call it. That looks like a lot of research and development, a lot of operations and maintenance. How'd you make that happen in terms of the funding?
Yeah, great question. It's a long story. I mean, so the Parcel project was funded by NSF about 8 years ago, and that let us
Okay.
build the Python parallel programming library that underlies the Globus compute agent. So that
Okay.
Parcel's an open source Python project. It's actually just moving to NumFocus as our sponsor home. So we're a sponsored project as part of NumFocus. We have roughly 120 contributors. That project is fairly solid as an open source code base. So a lot of the capabilities we have built on that. Globus Compute, we had the idea to build a federated functions as service system probably about 7-ish years ago. We thought, well, Parcel's great for running workflows on a single machine, but it's not so great when I want to run workflows across single machines. And there's this real difficulty of asking users to like manage SSH connections. They're just fragile and don't work so well. So we started building a servicified version of Parcel, which we called FunkX. We wrote a paper about it. It was actually nominated for best paper at HPDC. We got like the performance results. We did all the research stuff. We had some students in Yadu and some postdocs working on it. We did all the fun researchy bits, plotted some graphs showing it scaled well, hid the fact that if there was an error, everything would break and fall apart. And we wrote a proposal to NSF to sort of really validate that that's a useful model. So NSF gave us a 4 or 5 year project to really build that out, where the plan was turn this into something that the production engineering team in Globus takes over. So Reed and his friends take over, deal with all the stuff that we neglected to deal with on the build a pretty graph that shows scalability. So they basically threw away all our code and started again and built the system ground up. And our sustainability model was to get to the point where we have a good user community, where we have 100 people using it every week, where we can start building out that sustainability model. We decided to go with the Globus subscription model because of, as you point out, the significant resources that are involved on the service side, on the cloud side, for us to run this thing. We use a bunch of RabbitMQs, we have a bunch of S3 storage, Redis storage, so we have a pretty significant Amazon footprint. And the plan is that will be supported by our subscribers, and users will be able to make use of this platform without paying for it. So there'll be some limits. There are some limits on sort of how many tasks you can push through it at a given time. You've seen the limit on how much data you can push through it, etc. So we do have some limits to protect ourselves on the cost side, but the plan is that this is now 100% a Globus product. It falls under the Globus subscription model, so our subscribers are supporting the infrastructure to sustain the service for the good of the research community. I'm sure you didn't ask me for a life story, but you got it. You got it for free.
Oh no, that was great. Thanks.
It's a good question. It's probably one I have practiced that answer a few times. Maybe it felt polished, more polished than the rest.
I can tell you like answering that question.
If anyone knows Vas, I'm sure he'll be pleased with that, my great response. Any other questions? Yeah, do you just want to comment about what a great response it was?
That was all right.
What? It was right, okay.
It is all right.
You unmuted, so I figured you had something to say. Look, we're at 50% now. 12 minutes in, so if you all stick around for another 12 minutes, which happens to be exactly when the tutorial ends, this is like the fireworks at the end of the show. I'm actually supposed to be teaching a class right now, so probably we don't want to wait 12 minutes. I messed up the time. I didn't know there was the 30-minute break till recently. Other questions? Don't all go at once. No? Oh, there's a chat message. Oh, please fill out the survey, which I believe was in the chat. Yes, up in the chat, there's a survey. They would like everyone to fill it out if you could. Just wanted to say thank you, everyone, for attending. So it's great to have a good number of people here. The US-RSE is such an amazing community and conference, and I hope there's ways that we can work together. I think Globus Compute as a platform is really nicely aligned with the types of things that we often do in research software engineering. I think I would consider myself, Yadu, I'm sure would as well. Reed, I don't know if you've been exposed to RSEing, but I consider ourselves to be very much in the RSE community. So I think this is a platform that hopefully can help you with the types of science you're working with, particularly with building services and applications yourself, being able to outsource the complexity of this remote computing. Okay.
Just wanted to mention
go
too,
ahead, Reed. Reed
yeah, just real quick.
home.
So when you guys, you know, if you've already used this or if you're thinking about using it, we have a public Slack channel, and it's still in the FunkX Slack workspace, but the channel is help, so you can pop in there and ask us. Yeah, you go on funkx.org there,
Right
so you can go in there
Yeah.
and ask us. The whole platform development team is there, and we like to help people out, get people to use the product, and answer whatever questions. Also, just you can submit support tickets to Globus.
Yeah, that's really great point. So the Slack is very active. We have a help channel there that's used probably daily. It's the best way. All our development team are on there. I'm on there, and we are responsive. I think it's really interesting to see how people are using Globus Compute there and learn from what they're doing, learn from the types of questions they're asking. So I would strongly encourage you to join that Slack if you're interested in playing around with Globus Compute. And then, as Reed said, we have all the same Globus methods for support, which you can find on the Globus webpage. Okay, big thank you again, everyone, for sticking through this for 3.5 hours. We really appreciate it. Feel free to reach out to me or Reed or Yadu if you've got any questions afterwards. We'd be happy to set up a call to run through sort of your specific use cases and try and think about what features you would need, et cetera, et cetera.